Hello guys, am I audible? Am I visible? Is the screen visible? Can you do a thumbs up or yes on the screen? Okay, good. So we'll wait for a couple of minutes and we'll get started exactly at 5. Thanks for joining in. Okay, good evening all and thanks for joining. We are starting the session now. This will be a two-part session where we'll cover arrays and pointers in the first part and then we'll quickly cover recursion and structures. Now, when you have joined this session, I hope you understand why you have joined this session. This is not DSA. DSA, I have a separate series altogether in my playlist in the same YouTube channel that you are in right now. That's where DSA starts. This is more to do with you being C graduates now, you understanding C, and now how do you take the baby steps into DSA? What all from C do you need to carry so that you can be great DSA coders? That's what this session is about. So we cover only 4 things from C that is very important from a DSA standpoint, and those are the things that will take 4 hours for us to cover. I have kept it 4 hours, but I don't think it will go till 4 hours. As long as we are interactive in nature, we understand what is being taught so that I don't need to repeat. But then I'm hoping that we can finish it off within 3.5 hours. So there will be a break in between for 15 minutes after arrays and pointers is concluded, and then we will complete the rest of the session. So again, I'll repeat for people who have joined. or people who are watching this right now, the session here is not a DSA session. Don't confuse yourself to be a DSA session. Of course, I will take you from arrays, pointers, recursion, structures into the basics of DSA. We'll start telling you about linked list and how to probably start with linked list or conceiving linked list. But that doesn't mean I'll take you through the in-depth DSA session. This is not about that. This is an on-ramp session, which means it's it's a mechanism to give you a place into DSA as far as brushing up your C knowledge is concerned, which is required for DSA. Trust me, without these 4 things that you see on the screen, which is your arrays, pointers, recursion, structures, it will be very difficult for you to grasp DSA, right? And DSA along with system design is very hot topics for your campus interviews. So if you ask me about what topics do I need to study for campus interview, my first answer would be DSA. You being computer science graduates or computer science and allied stream graduates, right, your main bread and butter will be to code, and to code you need to understand algorithms, and for that you need to understand basics of DSA. So that's where DSA becomes very important. Companies evaluate you on DSA both from a coding standpoint, coding test standpoint, as well as from the interview standpoint. Trust me, it will be 50% of your interview. The rest of the 50% can be something else, but DSA will be 50% of your interview, right? And that's why I am putting this effort to give you back an on-ramp session so that you don't struggle when DSA courses start in your colleges, right? And of course, if you have joined late, the DSA series that is actually going to happen in this next 6 months or whatever 4 months you have in this semester, in case you are joining this from a semester perspective, then whatever time we have left till the next semester exam starts, till that point in time, what all DSA topics you need to cover and what are the lectures around it, you will find that in the DSA playlist in my channel itself. There will be a playlist which has approximately 24-26 videos exactly tailored to your university syllabus, exactly tailored to the PYQs that have been asked, and you can probably refer to that and understand DSA in and out. But before that, we'll have to complete this, right? So that's why we are all here. So let's start off with that note. And I know a lot of you would know arrays, would know pointers, might not know that much of recursion, might not know that much of structures. Some of the topics will be known to you, some of the topics will not be known to you, or some of the topics will be very hazy to you, right? But then this lecture is all about addressing the mass. So I will address the mass from the perspective that you know very basics about all these 4 topics, and from that ladder I will start crossing the heights of taking you towards the completeness of the topics that I am discussing. So what we are right now attacking is arrays. Before going there, a quick decorum check in terms of how you communicate with me. Please use the chat box. Unfortunately, I would have loved to open it up for voice chat, but I don't have that facility here. So please use the chat bot. And of course, you know my coordinates on WhatsApp. Any doubts, you can post it after the session on WhatsApp also. This deck will be presented to you on the WhatsApp group that you are in, as well as in the description of this YouTube live link. So please don't shy away from asking me questions. I will revisit the chat window every now and then as and when I get a logical break, and I will try to answer all your questions. Not try, I will definitely answer all your questions. Right, so let's start with what is an array, a very basic fundamental thing of what is an array. Let us say that you have 5 variables like this, that is int score 1, score 2, score 3, score 4, score 5. You are storing the marks that you have got for 5 students, right? So let's say you have been chartered to do that. You are storing the marks of 5 students here. So what is happening is you are actually creating 5 variable blocks like this, right, which is called as score 1 to 5, right? So this is score 1, this is score 2, score 3, score 4, and score 5. These are your 5 variables that you have created. Now imagine the situation where you are now asked to score it for the entire class, to score the scores or to keep tab of the scores for the entire class. Entire class is, let's say, 100 people, right? So if it is 100 people, what do? Do you create 100 variables, right? So do you create something like this, which is let's say score 1, and then score 2, score 3, score 4, and then dot dot dot, score 99, score 100. So this is 2, 3, 4, and this is 99, and this is 100. Do you do this? Is it manageable? Can you manage 100 variables? Right? You cannot. Right? Can you do calculations on these 100 variables? Right? Without increasing the length of the code? You cannot. Right? So there comes the concept of arrays. An array, please remember it. The thumb rule of array is that it should have the same data type. The same data types can be grouped together, right? The same data types can be grouped together. So I am taking let's say a packet. Let's say this is a horizontal packet. And inside this packet, what I am doing is I am taking the score 1. I am taking this score 1 and putting it inside this packet. I am taking the score 2 and putting it inside the packet. Score 3, putting it inside the packet. Score 4, putting it inside the packet. So this packet is actually what we call as the array. And these are called as my pockets. So let's call this as a packet, and this packet is the acronym for the array, right? Inside the array we will store the variables, right? So inside the packet we'll store the variables. So we'll attack the packet and not the individual variables inside the packet, right? If we have to attack the individual variables inside the packet, then it becomes the same solution as this, attacking the individual variables. So instead of doing that, what we'll do, we'll attack the packet, that is the array, and its job will be to attack the individual variables internally. I don't need to worry about it, right? I will store it in such a manner that it is inside a packet. So so the packet says that you are only supposed to give me the same data type. So the data type has to be the same. You have to have an int here, you have to have an int here, but you cannot have a char here. Not possible. So that's why I'm saying that it has to be the same data type. Inside the packet, you can only keep same data type variables, right? Next, the thing is that it has to be contiguous. It has to be contiguous. Contiguous in the sense that if this is an int, then the next block should also be an int. The next block should also be an int. The next block should also be an int. Right? So if you are storing contiguous elements, it means that you cannot have a situation where there is one more packet or one more memory area inside of which you have stored this particular thing. So for example, if this is your score 1 variable, this is score 2, score 3, score 4, score 5, and this is score 6, then this is a wrong pattern. This is not an array. Because this is one packet, this is one more packet, right? So which means that the two packets are not contiguous, right? So inside the packet itself, everything should reside. That is, inside the packet itself, everything should reside would mean that when you are actually talking of the RAM, so if I draw the RAM for you, if this is your RAM, then inside this RAM, if I'm putting these variables, then let's say this portion of the RAM is occupied, right? Let's say this portion of the RAM is free. Let's say this portion of the RAM is free. Let's say this portion of the RAM is occupied. Let's say this portion of the RAM is occupied. Let's say this portion of the RAM is free and the rest is occupied. Let's say the RAM is looking like this, and you are now tasked to actually create 5 variables. So the variable blocks you have is this 1, 2, 3, 4, something like this, let us say. Right? Now, if you have to create 5 variables, as I said, 5 pocket array, right? So we have to create this packet, and inside that packet we have to create 5 variables, and we have to create it in a contiguous manner, which means that if I take here one pocket, if I take, let us say, if I take this as my first element, second element, third element, right? Then my fourth element becomes non-contiguous. Therefore, the compiler will not select these to give you as the memory for the array. It will take this, and this. These are your 5 contiguous elements, and this is your packet. This is the packet that it returns to you. We will come to the address pointers, etc. as we go forward, but this is the packet that it returns to you. Right? Inside this packet, now you can store these 5 things. So you can store the first variable here, second variable here, third, fourth, fifth. So this is the packet that actually the compiler will return to you, because this is a contiguous element only available from the RAM. The rest are non-contiguous. That's why this block of memory will be given back to you. And you will use this block of memory to store the same data type. So these are the only 2 conditions for which you can create arrays. I hope that is clear. Right? So let me see the chat window. Please keep posting your doubts. Okay, nothing as such on the chat window. Now let's see how to declare an array. We know what is an array, what is the necessity of an array. So let's now see what is the declaration process for an array. So if you say that declaration process for the array, then arrays are declared like this, in which you can say that if you say int a5, then int a5 means the variable, that is the packet, is called as a. The packet is called as a. So this is my packet, and it has 5 blocks inside it. Each of the blocks can hold what? Can hold an integer. Each of these blocks can hold an integer. Right? So this is what int a5 means. So that way you have asked the compiler to give you a contiguous set of 5 pockets returned to you as one single packet, right, which is called an array, and you have asked it to be named as a, and this is what it returns you with. Now you are on your own to put values inside these pockets or indexes, as we call it, right, and that is how we start the array process or the array journey. These in C or in most of the programming languages, these elements that is inside this array, where you store the, or rather let's call these as variables. If I take the example of the variables, like the previous example that we took, right, we had said that these variables we will put inside this packet, right? So let us say that these are variables inside that packet. These variables, if you have to actually access, then of course you have to access it using the variable, the array variable a, and along with the array variable a, you have to tell me which integer variable inside it you want to access. The first one, the second one, the third one, fourth one, or the fifth one. So you may be saying a1 to actually refer to the first one, but C says that I am a zero index. C says that I am a zero index language, right? So whatever you give here is actually calculated after 0. So the starting point of the array will always be 0 and not 1. So this, while this is the count, right, and the index that we actually store in C is actually starting from 0, so it actually goes to 4 and not 5 as the largest size of the array. So the index is the way in which you will refer. So if you have 23 here as an integer, and you want to bring, you want to understand what is in the first pocket of the array, then you will say what is my a0, right? So a0 would mean that it will go inside this particular pocket and extract this 23, and it will return you this 23 from here. So you don't use a1, you use a0. There are other languages where one index is allowed, but for C we have it as 0 index. So please be careful on the index part. Now when I have defined this particular array, when I have defined this particular array as an array of 5, if I have defined A as an array of 5, what do you think their values would be? When this statement is executed, what do you think the values would be? The values would be very typical here, because the values you have not given. So this actually is coming from a larger RAM ecosystem, right? So there is a RAM here. The RAM actually has broken up into various blocks, right? Words we call it. So in this RAM, right, from this RAM, you have been given the contiguous 5 blocks Now why were you given these contiguous 5 blocks? Because they were empty. Because nobody was using it. That's why you were given it. Suppose this is getting used, this is getting used, this is getting used. Well, will you be given that block? You will not be given that block. You have been given this block because it was empty. Right? But was it really empty? If somebody else used it earlier and somebody else did not wipe it clean from the data perspective. So somebody had stored marks, let's say. Somebody had stored their marks. So somebody would have stored what? Somebody would have stored, let's say, their marks here, which means that somebody would have stored in an earlier program, someone would have stored, let's say, 23, 30, 17. These are your CA marks, let's say 25, 24. Right? Now you are defining A5. The program has ended. So this technically this area that an earlier program was using is free. Free doesn't mean that that area is clean, that it is blank. Free means you are free to use it. Imagine a plot of land where you have built a house and now the plot of land is available for sale. Does it mean the house is gone? The house is still there. It's not clean. The plot of land is not clean. Right? It's no more a land. It has a house on top of it. But it is for sale. Anybody can pick it up. So what does he get? He gets something which he doesn't need. He gets that house that he doesn't need. And that's why it's called garbage or junk. That's why it is called junk. So when you say A5, what do you get? You get garbage values. Inside what? You get garbage values inside A0, you get garbage value inside A1, and so on and so forth. So all of these will be garbage values. They will have some values. A0 will still store 23. A0 will still show you 23 because that is from an earlier program. Right? But it is counted as garbage from your current program standpoint. Current program may not want to store 23. So that 23 has no meaning to the current program. And therefore, it is called as garbage from the current program perspective. So I hope you understand what is garbage here. So this is how you need to understand when you initialize something, don't put any value, then what does C store in variables? Same thing applies to variables also, same thing applies to arrays, same concept. Now, if you say that I will do it in a different way, I will create a 5-pocket array, and in that I will put only 2 things, right? Then what does it do? It will create this B, it will put 1 and 2 here, and because you have taken the responsibility of assigning some values in the first 2 pockets, the compiler is intelligent to understand that the rest of the pockets it needs to clean up. Right? So that's why it will put 0 inside the rest of the pockets. I still don't agree with the compiler here because 0 is a number. It's not clean. Clean means blank, and there is nothing called blank in C. Right? So ideally it should have been blank for me. 0 is an integer, it has a weightage, it has a value. Right? So I don't agree that 0 means clean, but that's how C is. When you say 1, 2, you have taken the responsibility of what? This is called as declaration, and this is called as initialization. Right? Initialization. So in the first example, you have only declared. In the second example, you are initializing also, which means that when you are initializing, then the situation is that you have taken the role of putting some value there, and therefore the compiler is intelligent to say that, okay, you are putting values, that means you need a clean thing, right? Okay, let me put zeros on the rest. So that's why it does this. Right? So if you put, likewise, if you put, let's say int d5, and here if you put 0, then this actually means that you have created d5 like this, and 0 will be in the first pocket, right? Because this signifies 0th index, this signifies 1th index, so this also will signify 0th index. This is how you put the values into those small integer variables inside that array, right? So now I have put 0 in the first pocket. The compiler is intelligent to put zeros in the rest of the pocket. So that is what is on the declaring and initialization of arrays. I hope you have understood what is declaration and what is initialization. Let me go back. Ronak is asking, Macau third semester have DSA with CPP or DSA with C? DSA with C, Ronak. Ideally speaking, you should not get any code. It might have a practical examination. The practical DSA that you have paper, that will be on C, but then in the theory exams, ideally you should not get a code to write in C. That's again my personal view, but Mac out is Mac out, right? So my personal view is the topic itself is called what? Data structure and algorithms, right? The topic itself is called as data structure and algorithms. So it's an algorithm paper. How can you write a code for an algorithm? You can't ask code for an algorithm. That's coding. That's already gone. The C coding class is already gone. ESCS, what was that? 201. That's already gone. So for me, it's an algorithm paper. It should be asked as a pseudocode. It cannot be asked as a code. And I have seen papers where not a single line of code has been asked. Go back to your PYQs, you will see that. But I've also seen papers where C code was asked. So that's why I'm saying we have to live with it. And that's the sorry story of Macaut. But then Annesha is asking me, please repeat garbage. Okay, Annesha, garbage for you coming up. Let me use an area here. Let's say that I will use this area. So Annesha, if let's say you are talking of the RAM here, if this is my RAM and this RAM is actually looking like this, right? So I'm just taking a very simple example from integers. I'm not even going to array. Let's say you have defined int x equal to 7, right? Int x equal to 7. Let's say that the RAM was actually, these are all one integer blocks. Okay, let's say these every block. So I'm writing here every block is 4 bytes. 4 bytes means you can store one integer. So if you request the compiler to give you, so let us say this is blocked, this is blocked, this is in use. Somebody has used this, right? Somebody is using this. All these are in use. Okay, so let us say that this is the current situation of the RAM. The blank portions are remaining blocks where you can store what? 4 bytes of data. 4 bytes of data. That's one block, right? You have asked for what? Int x equal to 7, which means what? You have asked for 4 bytes to store an integer, right? Which you will call as x. So what does the compiler do? It finds 4 bytes blank here, right? And it will give you that 4 bytes back to you. So this becomes your x, right? So this becomes your x, and inside this what will be stored? 7 will be stored. Okay, now your code now runs here. There are several other syntaxes your code has, and then finally ends. Okay, when your code ends, then what happens to this RAM? It doesn't get cleaned up. So this RAM still remains like this, but it is no more called as x, right? So this program is complete. Your RAM is looking like what I am showing on the screen right now, right? Now what happens is another program comes, you write another code, you write that I want now int y equal to 23, right? So what it will do, this is free. This 7 is free because nobody is actually, the program which wrote 7 is actually gone, right? The program which wrote 7 is gone means this block is free for anybody else to use. So what it will do, the compiler will allocate this block to you, not this block, mind it. It will not allocate this block because the first block that it finds free, it will allocate. This is free. Why? You can ask me that 7 is there. Why is it free? Who wrote 7? Your earlier program wrote 7, which is now dead. So it doesn't have control of that memory. That memory is free. So now the compiler says, okay, this memory is free, but it doesn't touch the value inside that memory. It does not touch this 7. It only says this plot of land is free, right? So then it allocates y here. It allocates y to this variable, right? And then you say 23. So it will actually do a 23 replacement. Like this. This is what happens. Now, if you would not have said 23, and you would have just, then this would have not happened, right? So this would have not happened, and there would have been only 7 here, right? There would have been only 7 here. Now, what will happen here? Now, I am saying printf %d y. What will be printed? 7 will be printed. Now where did this 7 come in this program? This is my program. There is no 7 here. Where did this 7 come? Because it was from an earlier program. Has your program done anything to make it 7? No. That means for this program, 7 is a junk or a garbage. Right? So that's what is the definition of junk or garbage. Something that you have not done and is coming from a previous unclean surface or RAM or memory. Annesha, I hope this is clear. Okay. Hulk, I'm not understanding what your question is. If you can rephrase. If you are referring to other YouTube videos on DSA, as I said, this video is not about DSA. Right? And even if you are referring to DSA videos, which is available on YouTube, compared to the playlist that I have on DSA, I am not saying you watch my playlist at all. You are free to choose any playlist of DSA. My whole goal is to make you knowledgeable. Whether you do it through my videos, YouTube videos, which are better than my videos, I don't care. Right? So I don't understand the question. If you can rephrase the question, then probably I can answer you better. Okay, so now let's move on. Accessing and modifying elements of an array. If you want to understand how to access, modify elements of an array, then let's say that we have scores as an array, and that scores array is 5 elements, and inside these 5 elements you have 78, 92, 85, 63, 90. And these are my index positions of this particular array. So this is how my array looks like. Now I want to actually, let's say, read an element of an array. So if I want to read this 85 element or 85th element, then I will say scores bracket 2. As we all know, it is a 0 index. So if I want to read the 85th element, I will use this syntax, that is printf %d scores 2. Which will actually access this in a read-only manner. If I want to write something, as you know, if you have to write something into a variable, then you write it on the right side, right? Either you do this or you can say this, right? You are putting the value that you want to write on the right side. Similarly, for an array also, you will say that scores, let's say 3 is equal to 77. Then what will happen is this will become 77, right? So that is how you are actually accessing the various pockets of the array, indexes of the array, in order to make read and write transactions, right? So this is how you are progressing in terms of understanding, accessing and modifying elements. If we talk about the arrays in memory, how they are stored, right? So then we are now slowly getting into a situation where we will start pointers shortly. But before that, I just want to leave you with the concept where we are saying that if scores is here as the same scores array that we took earlier, which is going to look like this, then can we say that this has an address of, let's say, 2000. Address means what? Address means, again, go back to your RAM, and inside the RAM, let us say that this is how the RAM words look like, right? And these are your blocks of, let's say, 4 blocks, 4 bytes each, and each of these blocks have an address through which you can actually reach that block. Because if you want to reach this block, how do you know where this block is? Inside the RAM. You don't know. Similarly, if you want to reach to a plot of land, you would not know unless you know the address of it. That is why all access of memory is through addresses. If you know the address of the memory, you can reach to that address. So we are saying that, let us say the compiler, let us say this was all booked all these were used, right? And the only available area was this. So this was, let's say, 2000 as the starting address. This pocket was 2000 as the starting address. So the compiler says that I'm going to return 2000 as the starting address for this course 5, where 78 will reside in this 2000 starting address. I told you each block here is 4 bytes. So the next block will be at 2004, right? And that 2004 will have 2004 will have 92 here, 85 here, 863 here, and 90 here. So this will have 92, 85, 63, and 90, right? And the rest of the next set of addresses are 2008, 2012, and 2016, right? So if you want to access 90, you have to go to 2016. So how does it happen? How does it happen? It happens like this. If we say scores of 3, it actually means whatever is your base address, whatever is the base address. What is the base address? Base address is the starting address. This is my base address. So whatever is the base address, take that and then do this 3, take this 3 and then multiply it with what? It was an integer, right? So integer means what? Integer means 4 bytes. So multiply it with the 4 bytes of an integer. So what will you reach to is 2012. Right, so scores 3, 0, 1, 2, 3, scores 3 is actually nothing but at 2012, and this is how you reach to 2012. Right, so you take the starting address, multiply it by the index, multiplied by, or add it with the index, multiplied by the integer. For integer it is 4, for character it is 1, etc., etc. So it's simple. You are actually skipping that many number of integer blocks from the base address in order to reach your index. So this is how arrays are stored in memory. So they have an address because it is contiguous. That is the reason it is contiguous. So that 2000, the next element is always at 2004 if it is an integer. Otherwise it would have gone somewhere else. It will not be contiguous. It has to be beside it. 2004, 2008, 2012, 2016 array is done. Right? So that's how you are actually accessing the or addressing the array in memory. Let me go back to the chat window. Let's see if there is anything else. Nothing more on the chat window. Let's go ahead. Okay, now traversing an array from a standpoint of how do we have created the array. Now how do we traverse the array? Now traversing the array means that if we take the same array, let's say scores, and inside of scores we are actually putting these elements. So 78, 92, 85, 63 and 90. So if you are putting this, and these are my index position 0, 1, 2, 3, 4, then if we do this integer loop that you see on the left, if we do this integer loop, it means that at a position of I, if I say I, then I starts from 0 and I goes till 5. So I will go till like this, 0, 1, 2, 3, 4. So I will go like this. And what are we actually checking? We are checking scores of I. So we are actually checking scores of I, and that means that the first check here will be of scores of 0, right? So scores of 0 goes to where? It goes to a variable called sum. So sum here will be, if you see the sum value here is 0, right? So if sum is 0, you are saying sum, whatever is the sum, add it to scores. So sum was 0 and scores of 0 is 78. Right, so I hope you understand this is nothing but 78. Next, what happens is it goes to the loop again and then it takes scores of 1, right, because I is 1. So at the 1 it has 92. So 0 plus 78 is already stored inside of this. So it has 78 and it will add 92 to it. Right, and this is how you will actually go through the array and you will do whatever you want. In this case, I have done the sum of the scores. So instead of summing up 5 different elements, I did it through a loop. 5 different integer variables, I did it through a loop. If there were 100 integer variables also, the same code would have worked. Only thing is change the boundary condition. Right. So this is how you traverse the array. You typically will create a loop and you will run from the index that you want. In this case, I want it to start from 0 and I want it to end till the length of the array. You might have different conditions depending on the use cases, so your loop might look different, but the basic principle is going to be the same, right? So you will have to use this I intelligently as an index mechanism. So this is all that matters. Take your I and increase it so that it refers to this index, and then use that to your advantage in order to read and write from those indexes inside the loop. That's how the traversing of the array typically works. Now, if we talk about the bounds of the array, right? So bounds of the array would mean that we are actually given a block of memory and nobody is stopping us from actually accessing beyond that block. What happens to that? So let us take the same example. Our RAM compiler had given us this from the RAM, right? So let's say it had given us the 2000 address from the RAM. So this is my scores, same variable, right? And this actually has 78, 92, 85, 63 and 90. So this was at 0, 1, 2, 3, 4. Now I'm saying that I want to access what? I want to access scores of 5, right? 5 is here. What happens in scores of 5? You have understood previously what I said when I said that take the base address. When I say scores of 5, what happens is 2000 is my base address plus 5 multiplied by the size of an integer, which is 4. So this goes to 2020. So 2020 will be this position. Let us see that. This is 2004. This is 2008. This is 2012. This is 2016. So this definitely is 2020. So this position that we have here is something that the compiler did not give to you. And you have intelligently or non-intelligently gone to that position. What will happen? The compiler will not complain. It will not complain that you are at an out of bounds. It will not complain about that. It will only say that you are in fact, it will not say anything. What you will get here will again be garbage, because you might have gone into some other program's memory space. You never know, because this is probably going to be how the RAM looks like. So if you see, the RAM might be looking like this. So this area that you have gone is actually not accessible for you. These were already blocked areas. Why have you gone there? So that is where you will again get a garbage value. So this actually returns a garbage value. It's not supposed to be there for you, but you have gone there. Fine. Compiler doesn't stop you. You will get a garbage value. Right? So this is what is on the array bounds topic. Now the last topic of arrays is on the fact that we have to touch upon character arrays, because so that we can process strings in our DSA logic, right? So that's why I'm touching upon character arrays as a string, right? So now it's a bit different for you to probably understand from an integer array. I'll just compare integer with character arrays. So bear with me. So if I say scores as an integer array, so int scores, if I say 5, and if I put my integer arrays like this as the scores, and the scores are again in a scale of 30, if I do the scores, then the scores may look like this, right? Now compare it with a character array. Compare it with a character array where I want to store a name. So char name, right? And this name, char name, I want to store, let's say, Aman. And if I store it like this, A, M, A, N, right? I will store it like this inside the character array. This is my 0, 1, 2, 3, 4 index. This is my 0, 1, 2, 3, 4 index, or 3 index. Now think about it. Hear me out carefully. When you have the scores here, and you have this particular array that is created out of scores, do you think you need to access all 5 scores in one shot for a meaning? For deriving a meaning, do you need to access all 5 elements in one shot? You may be accessing 23 as the score of the first student. You may be accessing 20 as the score of the fourth student. But do you want to access all 4 in one shot and it gives you a special meaning? No, right? Each of these are individual scores which can talk individually, that I am the score of the first student, I am the score of the second student. So basically all 5 of them put together will not throw any special meaning, in a different meaning. But then compare it with this. Do you think A has any existence separately? Like 23 had an existence that it was the score of the first student. A doesn't have any special existence. A is part of the bigger name Aman. The entire thing now becomes important, unlike the integer array where the entire thing was unimportant. Only the individual elements were important. But here the entire thing is important. Right? So the entire thing is important means you will probably not access the first element, second element, third element, fourth element. Here you will access the first, second, third element in the integer because they are scores of individual students. But these have no meanings. So you are not going to access these separately. You will access the entire array at once because you want the name, not the characters of the name. Right? The characters are there for you to access, but will you access? Most of the times you are going to access this at in a holistic standpoint, which means you will not use the %C format specifier, but you will be using a %S format specifier, which stands for strings. As soon as you do it, right, if you do this now, let's say this, printf %S name. So this is my name. Printf %S name, what will it do? What is names? Let's say this is starting with an address of 2000. So this is a character array, so this will be 2001, 2002, 2003. So what or how will printf %S name behave? Let us see that. So if you see the RAM, right, if you see the RAM of this, then the RAM of this may look like this. And inside the rest of the positions of the RAM, there could be so much of things. Let's say here there is 27. Here there is another A. Here there is some value which I don't even know, some ASCII value, right? I don't know that. Now, when I say printf %S name, how does printf behave? It goes to this 2000 address and it prints A. Then it increases the 2000 to 2001 because it is a character array, right? It knows it has to increase it to, so from 2000, so let us say it says 2000, it will print A. It will go and increase it to 2001, it will print M. It will go and increase it to 2002, it will print A. It will go and increase it to 2003, print N. Now what happens? Now, why will it stop here? What is so different for it that it will not go to 27? That is something that you have to realize. So it will not stop because for the compiler, this and this has no difference because this is also one pocket in which there is 27, let's say. Right, so it will go ahead there and it will print whatever is there. I've simplified things here. I've put a 4-byte thing beside a 1-byte thing just for a simplification perspective. Assume that it will print 27 at a 2004 location. And this will go on forever. This will go on forever because it doesn't know where to stop. You might ask me, why doesn't it know? I have given char 4, but how does this happen here? Notice name. Name is actually nothing but the starting address of this array. Okay, so that's the most important point that I wanted to touch upon. Please remember this. The name of the array is the starting address of the array. That is what I wanted to convey. Now, which means that what does printf know? Printf knows what? 2000. It doesn't know anything else. It doesn't know name is a 5-character array. So that's why it doesn't know that it has to go 5 blocks, 4 blocks. It doesn't know. Name of the array is the starting address of the array. So all it knows is the starting address. So it will only have starting address at 2000 here. So from there it will go here, here, here. So it needs a stopping condition. And that stopping condition is this, which is called as the null terminator. So if while creating this array, if somehow I put this null terminator here, if I somehow put the null terminator here, this is basically the stopping condition of that array, and therefore this has to be changed from 4 to 5. Right? So I hope now you understand that string arrays or string, which is a character array, is to be treated differently from an integer array, because for a string, the string matters, not the characters. Right? But for an integer array, there is nothing called an aggregated integer. Only the individual integer elements matter. Right? So I hope now you are getting a hang of what is string and how does string get processed, or why does string need a null terminator here. So this is how we will conclude arrays, and that's all that we will need from an array standpoint as we come along. By the way, this is not a formal array class or something. I'm just touching upon what all you need from a DSA standpoint. So always take this lecture from that pinch of salt, that this is not any and everything on arrays, right? It is only about getting you on ramp into DSA so that you don't struggle figuring out what is an array, right? So with that, we will get into pointers here. Let's see what all has come in here. Okay, I don't have anything on the chat window. So let's move on to pointers. In a pointers, most of you might be afraid of pointers. Some of you have already grasped it. But let's take an attempt on why pointers first, and then we can move on from there. So if we see what is the pointer concept from a necessity perspective, then think about this code. This code does what? There are two variables x and y, and it is trying to swap these two variables, right? So what happens from a memory standpoint? Let us see. When I say int x equal to 5, then there is a variable block that is assigned to me for 4 bytes, right, by the compiler, as you know probably by now. And let us say that that is x. This is at 2000 address, and it contains 5. And this is a block of memory that I have inside my main, right? So main has, each function has its own block of memory from the RAM. Other functions cannot see each other's blocks, right? So this is the block of memory that I have from my RAM. Next, I have y, which is going to be 10, and this, let us say, is at 3000. These need not be contiguous because they are individual integers. So that's why I didn't take 2004. Now I say swap x and y, and swap is a function. So swap says I need some memory. So swap goes to the RAM. RAM gives it a memory. What memory does it give? Swap says I need memory for this, int a and int b. So there is an a variable here, and there is a b variable here that the compiler gives it, right? And when I have said x, it means I have passed 5 here, I have passed 10 here. So which means this 5 will go inside here, and this 10 will go inside here. Now I'm saying that there is a temporary variable called inttemp. So there will be a temporary variable, and in this temporary variable I'll be keeping a, right? So this is 1 minute. Yeah. So in this temporary variable I will keep my a. So when I say I'll keep my a, that means this comes here. And then I'm saying a equal to b, which means that the content of a will be replaced by the content of b. And then I'm saying b equal to temp, which means content of this will be replaced by this. Now the code ends here, and it comes back here, right? Did the swap happen? Whatever was there inside main was never touched. I touched what? A copy of main's variables, right? So I touched a carbon copy of main's variables. So everything that was touched after this swap function, this is the swap function. So when it returns back into main, so when it returns the entire memory that it consumed is lost. So the entire memory of a and b is lost, right? So you cannot access a and b from within main because it is inside some other function's program space, and because swap has also returned, those memories are now redundant. They cease to exist. And that is why when you try to query what is my x and y after this swap has happened, it is still addressing the memory of main, right? And the memory of main has never changed, and that is why the swap here does not work. And which is why we need a necessity not to carbon copy, but to take that particular memory location rather than the value inside of this swap. So instead of saying that we need a carbon copy here, instead of saying a carbon copy here, we will have to say that why not take the location of that variable here? Why not take that location here? And that is the necessity of pointers. So if we now get into pointers and try to understand where we are coming from. So let us say that we have int score, which is 78. Now this has a pointer or this is stored inside an address called as 1000. Now if we have to understand what is this address and play around with this address, then we need to have a variable that can store this address. So we need to, if we have to store this address somewhere so that we can play around with it, so that we can go to that address, we can do something with it, we can add to that address, right? Then we need to store it somewhere. And that storage is pointer. That's all it is. That storage area is called as pointer. In this case, we are calling it as P. So if this 1000 can be stored here, then P becomes a pointer. Because P is a pointer, it needs to be specially treated with a star symbol. And what kind of variable it is pointing to? It is pointing to an integer variable. So that is why you have to define P with int star P, right? And then say that my P is equal to ampersand of score, right? So with these two syntaxes, you are actually making sure that your P and score are actually now tied together. How? We are saying that we will create a pointer variable called P. Okay, so this is my pointer variable. We are saying because it is a pointer variable, it cannot be treated like a normal variable. Give it a special number or a special sign. This is that special sign, which is called as the special sign for the pointer variable. Now you are saying this variable points to an integer, right? So therefore it should be called as an integer. So this is the three dissection of the three syntaxes inside that pointer. Now once you have understood that this is how pointers are done, then how do you bring this value inside here, right? This value comes using the ampersand operator. This is called as the address of operator. So what is the address of score? This is what this line is saying. What is the address of score? The address of score is 1000. So we are actually saying P equal to 1000. Right? So ampersand score actually brings out the address from the score variable and therefore gives us this address. Now once this is done, this address is done, once this address is actually bucketed inside this particular pointer variable, now the pointer variable is self-sufficient to actually do whatever it wants with this pointer. Now I can print the pointer. If you want to print what is there in this 1000, then you will use %p. Right, so this is the format specifier for printing the pointer. As I said, pointers are hexadecimal numbers which are very long, therefore there has to be a special treatment to it, for which, as I said, that you will have to use a star p instead of a p. And as soon as you're using star p, you cannot use standard %ld or %d as format specifiers to print the pointer. You'll have to use %p. So that is on the pointer. But then what can you use the pointers to actually now achieve? So let us see what all we can use the pointers to now achieve. Same example, let us take that we have taken 78 as the score variable, and this 78 score variable will have a pointer which will point to it, and it will be called as P or star P, and it will have the address of this 78, which let's say is 1000. So this is what is happening here through these first two syntaxes. I have created the score variable 78. It is at an address of 1000. I am doing ampersand of score, which means address of score. Address of score is 1000. So this 1000 now goes into P. So that is what is happening here. So this is also a variable. Don't forget, this is also a variable. It also has an address. It also has an address. It's a variable again taken from the RAM. What you store is different, right? So it stores integer, it stores a pointer. That's all it is, right? But it's still a variable. Now, once you have this, and then you are saying that star of P is equal to 99. That means that go to P, right? Go to P wherever, or go to P. First of all, let's say this P means what? If you go to P, what do you get? You get 1000. So P actually means this for us. Now you are saying star of this 1000. That means that you are saying dereference from this pointer to the value inside that pointer. I don't want the pointer, I want the value inside the pointer. So star is actually acting as a dereference. So this way, if you understand that this pointer is pointing here, that means it is referring to this, right? So this is referring to this. But if I say dereference, it means that your address that you are referring to, you'll have to translate that address to the value inside that address. So that's where I'm saying that star of 1000 means the value inside that. So the value inside that is what? The value inside that is 78. What are we saying to do with that 78? Change it to 99. So that's what we are saying, that this is equal to 99 means that here whatever is the value at that address, change it to 99. So the dereference is also called as the value of operator. So it's either called a dereference operator or the value of operator, which signifies that at that address I am not interested with the address, I am not interested with this, I am interested with what is the value at that address. So go from here to the address, because this is 1000, so you know how to go from here to here. I am here. How will I go here? Because I have already been given an address. If you are given a chit of a location, a Google Map location, you can go there. So we have given it the Google Map location, go there. So it goes there. And then what did we say? Change it to 99. So it went there and changed it to 99. That's all it did. So that is what this reading and writing through pointers is all about, right? So I hope the ampersand and the address of operator is understood by you, or rather the value of operator, the dereference, the reference, all these are technical jargons which you may or may not be asked during your interview processes. I hope that is clear. Now if I go into the concept of null pointers, then from a null pointer perspective, let's see what are the various mechanisms or what are the various errors that you might be doing while doing pointers. So in terms of null pointer, int star p, what is int star p? Int star p is going to return to you. You are saying that I have a pointer here which is called as p, sorry, this is star p here, and you are saying that this will point to an integer. Where is that integer? Where is that integer that it is pointing to? There is no integer that it is pointing to. So which means that it has, by the way, as I said, whenever you define a variable and you don't associate it with some value, it will always contain a garbage, right? So it will always contain a garbage. So if you have defined a pointer, then it will always contain a garbage. Let's say it contains 31798. So that is where it will refer to. That is the location it will refer to, 31798. Some garbage, right? Because you have not associated to it. What is the earlier RAM content? Will come back to you. 31798. So it is pointing to 31798, right? And this 31798 can contain something. I don't know. Whatever it contains. Did I want this? No. If I had not wanted this, then therefore this is also a garbage. Did I want to point here? No. So this is also a garbage, right? So that's why when you say int star p, always define it with an address. Don't keep it dangling like this. Otherwise it becomes pointing to a garbage address. Now if you don't want to point it to a garbage address, then do it like this. Int star q is equal to null. When as soon as you do null, it points to 0, and 0 is a reserved address, right? So 0 is not an address where you go and see junk. So it always points to a reserved address where nobody can go, and that is what you are trying to say, that I have defined my pointer, I still don't know where it should point, I am therefore saying it will point to 0, right? And the other thing that you need to safeguard while using pointers is that if there is a q, you need to check whether q is not equal to null before actually retrieving the value from q. This is the value of operator, you know by now. So before actually saying that printf, let's say %d star q, right? We will have to check that, or not while, let's say if it is just a single line check, then you may check with if q not equal to null, that means Q is not having this. That means what? Q is having a valid address. Q is having a valid address like this. Right? Q is not equal to null means Q is not equal to 0. Which means that now it has a valid address, and that valid address will go into, or that valid address will be something that you will need to actually go through your program. If you say star P equal to 5, something like this, if you say something like this, what will happen? Now see, star P, where was star P? Star P was defined as a null. Star P was defined as a null. So it was not null, star P was not defined, which means it was having a garbage value. So going into a garbage value and putting a valid value is not allowed, and hence the program will crash. So these are the 4 or 5 things that you need to remember, because you had not initialized star P to a proper address, and it was holding some junk value, right? It may or may not point to a proper area of the RAM also, for all you know, right? Because that is just a value. That value could be anything. It may go beyond the RAM also, right? Because that value was, suppose the population of India somebody stored there as a value. So the population of India will now come as a value for the address, and that's a huge value which may not be available in the RAM at all. RAM that cannot be an address of the RAM. It's a value of the population of India. That's why I'm saying that the compiler actually treats it as a crash, because you have not associated it with a proper RAM value, and hence putting star P equal to 5, it doesn't know where to go, and therefore it will crash. So that's on these pointers in terms of the what you need to be careful about. In terms of the pointer arithmetic, and this is where it becomes interesting, because now we will talk about arrays also and pointers, and that's where we will see that how arrays behave with pointers. So now if you have given scores, the same example that we were doing earlier, and this is actually 5 pockets: 78, 92, 85, 63, 90. Right? So if you are doing these and you are actually having 0, 1, 2, 3, 4, these are the indexes that you have, and here you are actually saying star P equal to scores. Now what is happening? Just try to understand what happens here. Some of the knowledge that you have will be undone if you go through this, right? So what is happening here is, as soon as I say scores, right, something happens here which you have not understood till now. Forget about pointers. What happens is, when you say I want to define a scores of 5, it defines something like this. I told you the name of the array is the starting address of the array. The name of the array is the starting address of the array. If the name of the array is the starting address of the array, then the name of the array should also be a pointer. How can it store an address if it is not a pointer? Right? So if the name is storing an address, then it should also be a pointer, because the pointer can only store an address. So actually speaking, there is nothing like this that gets created. You actually have something like this getting created. A pointer called as scores, which has 1000, which is pointing to a block, which is your packet, where you have stored all the integers that you want for the scores. Right? So this now becomes 1002, 1004, 1008, 1012, 1016. Now pointer arithmetic says that you can only do plus and minus. You cannot do star and division. These are not allowed with pointers. So if you have 1000 as a pointer inside P, then P itself is 1000. So I said I can do plus. So can I do a P plus 1? So does it, if P is 1000, then P plus 1, does it become 1001? May or may not, depends on where this P points to. This P points to an integer array, which means that each block that the pointer should go should be 4 bytes in length, right? So these are 4 bytes in length. So when I'm saying 1, I'm saying 1 block, or I'm saying 1 multiplied by size of an int. Both are the same, right? So what it means is, therefore this gets translated into 1000 plus 4. Eventually it gets translated into 1000 plus 4, which is 1004. So when I say 1000 plus 1, where does it go? It goes here, because now the pointer is now pointing to 1004, because 1000 plus 1 evaluates to 1004. Therefore this changes to 1004, and when this changes to 1004, it now points to 1004. Eventually, if you want, you can change the starting address also, but typically don't do that. We will not do that to change the starting address. We'll say that we want to access 1004 without changing the starting address. Let's scores be at 1000. So we will say that scores, whatever you are, you add 1 to it, which means 1 block, and print it. And print it with %d. Okay, now what is scores plus 1? Scores plus 1 is an address, so I cannot print it with %d. What I wanted to say is, I will print the value at that scores plus 1. So this is what I will be using to print. It is the same as saying scores of 1. Right? What is going to be printed here? Achha, what is scores? Scores is 1000. What is plus 1? Plus 1 means plus 4. What is that? 1004. What is that? Then we are saying star of 1004. That means go to 1004. I'm not interested in your address. Dereference operator. Go to 1004. Get the value. What is 1004's value? 92. So what does get printed? 92 gets printed here. Compare it with this printf %d scores of 1. What gets printed here? 92 again. Right? So what is getting printed here is actually the same. Both of them are the same. So there is, if you ask me, there is nothing like this in C. This was given for our own convenience. Everything happening behind the scenes is this. Right? This is what is happening. So do you see a parity? Do you see a parity which says scores plus 1 star is the same as score 1? Right? So you see a parity here. Therefore, you also see a parity here saying that, okay, scores plus 1 star, if it is the same as scores 1, then definitely score 3 will be the same as score 3 here. Right? So eventually, can you say that star of 3 plus scores is the same as score of 3? Of course, I can say that because addition is commutative. This is the same as this. I've just interchanged the positions. At the end, what is happening? 3 blocks is getting added to score at the end of the day. And then we are doing a star, which is the same as this. So, all of these mean the same thing. Star P plus 2, P2, or we can do like this. This also means the same thing. So, don't forget that if in the interviews you are asked, what is star a pointer, star of a pointer plus, let's say 7, immediately you can write it is P7. Or if they ask you what is star of 10 plus pointer, immediately you can write it as P of 10. And the reasonings we have just now explained. Right, so that's something on the pointers and arrays that we wanted to talk about. Now the last thing on pointers that we will talk about, let me go back to the this one chat window. There is nothing on the chat that I can see. Okay, fine. So pass by value and pass by references. If you see this, this is the same problem that we started with when we started pointers. Now we are saying that we are going to have a pass by value and a pass by reference to solve the problem that we started with. So we will say that let's say we have a variable called a, and that has 5, and we have a pass by value function, and this is inside my main block memory. This is inside my by value functions memory, and we have one more block of memory which is by ref. Now A5 is at an address of 1000. Now by value, when I say by value here, by value, that is I'm making a function call and I'm saying that I want to call you with a. That means there is a necessity to create a variable in the by value address space with, let's say, 2000. and I am saying that this A goes into this A, right? So that means this is a carbon copy that will go in. So we are talking about a carbon copy here. Whatever was there in the mains A now goes into the by value function areas A variable. Both the variables can be named separate, but they are actually different because they reside in different locations. Think of these as two cities having the same address, right? So two cities may have 20 by 3 MG road. Here also there is a 20 by 3 MG road. So these are the two cities having the same address. So that's how you're having two same variables but in different locations, and you have made a carbon copy from one city to another or one location to another. And now you are saying by ref of ampersand A. Now by ref ampersand A means that this particular by ref function says that I don't need a variable but I need a pointer. So that's where the compiler will give it a pointer variable to store addresses. So this itself might have its own address, but it will store what address? Ampersand A. So what is ampersand A? Ampersand A is the address of A. So it will store address of A. So here is where I'm saying that I'm going to send you the location now. Rather than sending the carbon copy, that is the value at that address, I'm going to send you the location of the main. So the main's location is now exposed inside the byref function. So the main variable's location is now inside the byref function. So if you have the location inside the byref function, now you can actually say that I will do x equal to 99. If you do by val x equal to 99 here, then what will happen is by val had a variable called x. So let me also name this as x. So by val had 95 inside it, and I'm saying that I'm going to change it to 99. So be it, 99 changed. But did A change? A did not change. But if I say that here I will say star x equal to 99, right? If I say star x equal to 99, it means what is x? X is having 1000. What is star of 1000? Star of 1000 is the value at that 1000. So it goes to this value at that 1000, and then it does 99 change here. So this is what happens. It goes to that value at that 1000 and changes it to 99, and therefore you now have a pass by reference which changes the original content of the variable. So that is how you solve the problem of swapping the numbers. So with that, the last topic, probably this is the last topic. Let me see this. Okay, there is a pointer to pointer and triple pointers with which we will probably be ending it. So let's say that we are talking about a function now, and this function that is supposed to return an array. So how do we pass an array to a function? How do we return an array from a function? Now if you see that I have told you array name is a pointer, right? So array name is a pointer. That's what I told you. So if I have scores as an array and I am inside my main, this is my main, and I want to call a function called bump, and I want to pass this array. As soon as I do this, what does it mean? What am I passing? What have I written here? I have written scores. What is scores? Scores is the name of the array, right? So what have I passed? I have passed the address of the array. I hope you are understanding, because the name of the array stores the starting address of the array. I have passed the starting address of the array. So how does bump need to look like? How does bump need to look like? The function bump is getting what? An address. It is getting an address. So it needs to actually store this address inside a variable called as A. So bump needs to store the address inside a variable called A. So it can be defined like this, so that this address now gets passed here. Or I can also say that bump can be defined like this also. You can simply define it as a blank array, which means at the end of the day, scores is pointing to an array only. So put it inside this variable which you have defined as a blank array, or put it inside a pointer, because what you are getting is the address of the array, right? So now you have understood that because the array name is an address, if you pass it to somebody, the somebody has to catch it by either using the array syntax like this or by the pointer syntax like this. Right? With that, after that you can change it whatever way you want. Now let's understand double pointer and triple pointers here, just to make sure that we have consistency, because double triple pointers will be required when you do various kind of data structure in terms of stacks and queues. There are certain areas where we will require double and triple pointers. Not triple, double definitely will require. Right? So if I say that if I have int I equal to 3, then as you know, 3 is here, I is here, let us say its address is this. Now I say that I will create a pointer called j, which will start pointing to my I. Then this pointer called j should have ampersand I, which means the address of I, which means it will have 1000. It itself has its own address because it's again a variable of its own. Now if I say that I want somebody to point to this, then I will create one more variable and I will say it will contain the address of j. It will contain the address of j. What is the address of j? 2000. So it will contain 2000. It itself has an address. What do I call this? I call this double pointer of k. Why double? Because it's a pointer to a pointer. Right? So it's a pointer to a pointer. This is a pointer to a pointer. That is why double pointer. Right? So that's the reason. Now if I say what is the value of I, you will say value of I is 3. If I say what is the value of star j, what is star j? Let's see. Star j means, what is j? J means 1000. Star j means I am not interested in your 1000, go to 1000 and get the value. So star j means what? Star j means 3. What is star k? Star k also will mean 3, because I am saying that the first star, if you see, what is k? Let's do this. What is k? K is 2000. You have given star. So k is 2000. Now let us do 1 star of 2000. 1 star of 2000 means that I am not interested in 2000. Go to 2000 and get me the value. What is the value at 2000? 1000. So then this evaluates to what? This evaluates to 1000. Then what have I said? I have said this. Right? So I have said this here. So which means I need star of 1000. So if I need star of 1000, it means that I will go to star of 1000 means I will go here. I am not interested in 1000. I want to go to the address of 1000 and the value that is contained there. So this actually means for me 3, and that also matches with this. So whether you do I, whether you do star j, whether you do star k, it eventually will all go here. Right? Let's take another example. Let us say that if I say and I, what is and I? And I is 1000. That you know. Ampersand of I means address of operator. What is j? J also has 1000. Right? And what is star k? Star k means what? Star k means whatever is there in k, I am not interested in that. Whatever is there in k, I am not interested in that. I want to go there and see what is there as a dereference operator, which gives me 1000 again. So this is also 1000. So all these are also the same. If I say and j is 2000. That is the address of j. If I say k, what is that? That is also 2000. So these are also same. So there are various ways in which inside a double pointer or a triple pointer situation, you can use any of them to actually traverse to the data. That is an intelligent usage that you'll have to think of. Now triple pointer is also going to be the same thing. So I hope I don't need to do this in details. We will have I 3000, some pointer will be pointing to it, which is, let's say, j, which will be at 2000, and this will be pointing to 3, means it will have the address. Now here there will be one more pointer, which is k, and this k will have an address of 2000, and it itself will have a 3000 address. So this is my star j, this is my star k, and then we will have one more pointer, which is your star m, and which will be pointing to the address of 2000, which is 3000. So this is your triple pointer situation. From here you can do the arithmetic that I just now taught you in the previous slide, and you can actually reach to any of these variables using star, star m, star k, right? You can use any of them. Just do the mathematics the way I segregated it out and told you to do. You can actually reach there. Now this particular topic that you will have, this is the last topic on dynamic memory allocation. So this topic that you will have will be important, very important from your DSA perspective. So that's why I've kept this here, dynamic memory allocation. Sometimes you don't know at the time of creating an array that you need 5 pocket array or you need a 500 pocket array. At the time of writing the code, you may not know. So what do? You actually will rely on doing a compile time, converting the compile time array declaration to a runtime array declaration. That is, during the runtime, I will accept from the user how many array pockets do I need to create? 500. Okay, let me create a 500 dimension array. But your normal array syntax will not allow you to put a variable here. So you could have easily said scanf, right, %d into an ampersand of length, right? That is the length of the array that I want. So you could have said here printf, let me say, make some space here. I could have easily said printf enter array size, and I take it inside length, and then I write that int arr bracket length, right? You will get an error here. If this was okay, you didn't need to have malloc, right? This is what is dynamic memory. You want to do this, but you cannot do this with this syntax, right? Because this is getting captured at runtime. You are trying to create the array at runtime. So now what you will do is you will say that, okay, forget it. I'm not going to create it with this syntax. I'll create it with a different syntax. I know there is a friend called memory alloc or malloc. Now malloc says, how much memory do you need? Malloc doesn't care about integer, character, float. It just says, how many bytes of memory do you need? Tell me. So you needed what? 500 multiplied by, let's say, 4 as the integer size. So 500 is what you need, let's say. So this length, the user has entered 500. I need 500. So then 500 integers is needed. 500 multiplied by 4 bytes of space you will need, which means you need what? 2000 bytes. So you will say to malloc, I need 2000 bytes. Can you tell malloc length multiplied by size of int? Instead of saying 2000, you say length multiplied by size of int. So this was your length and this was your size of int. So it's perfectly legal. This is an expression. This expression will evaluate to 2000 only. So it will go back here only. So it is perfectly legal to tell malloc either the actual byte or an expression through which the actual byte can be calculated. Now malloc will go to the operating system and ask it that where is a free slot for 2000 bytes. Now that free slot for 2000 bytes is, let's say, at an address of 3500. Here is where that free slot is. So malloc will say, I am returning you with 3500 as the address where you can position whatever you want to do. Inside of 3500, you can actually use 2000 spaces, 2000 bytes. From 3500, you can use 2000 bytes. 3500 is your starting location. Right? So that's what you actually do when you are saying that malloc, when you say int star p is equal to malloc size of int. So we are saying that I want in this example that you are seeing here, it is saying that give me only what? Give me only 1 byte or one integer element, 4 bytes. 1 integer, 4 bytes. So give me 4 bytes of space is what it's saying, right? Size of int 4 bytes. So 4 bytes will be like this, 4 bytes of space. This 4 bytes, let us say, starts from 1000. So this 4 bytes of space which starts from 1000 is now returned inside the pointer p. So there is a pointer p here which will now store 1000, and therefore it will start pointing to that address. This is what is happening. So you can actually say 4 bytes, it will point there. You will say 2000 bytes, it will point to a space where you can use 2000 bytes. So the way you use it is up to you. How much memory you need is completely up to you. So once you have that star p equal to 1000, you can actually do star p equal to 42, and then that would mean that at that 1000 I want to store 42. If I say star p equal to 42, what will happen? It will say that I don't care about your p. This says I don't care about your p, I don't care about his 1000. I want to go and dereference this, go there and store 42 here. So that's how you can use malloc to actually create pointers or to create runtime memories. Here, if you would have used this example, then what would have happened? Let's see. If you have used this example, then malloc, we would have written int star, let's say arr is equal to malloc, let's say length multiplied by size of int. And this would return us with what? It will return us with an array, arr, right, which is a pointer. And this malloc, as I said, has returned 3500. So 3500 will be the return. So we are actually pointing to 3500 like this, where I can store 2000 bytes of memory. So this is what is happening when I say that int star arr equal to malloc of this. Now inside this 2000, I will store 500 integers, so be it. I want to store 2000 characters, so be it. Right? A lot of modern compilers are actually doing this, where you don't need to typecast this, but malloc typically wants you to typecast also. So if you see that malloc has returned you with 2000, it doesn't even know what you are going to store there. So how can I say that I will put this as an int, right? So I need to probably do a typecast here. So you will have to create a typecast here saying this is int star. Right, so that typecast is required, but a lot of modern compilers are intelligent enough to see the left hand side and typecast it automatically. So which is why this example doesn't show you the typecast, but it's safe to give you the typecast because malloc has just returned a memory. What inside that memory, nobody knows. Malloc doesn't know, doesn't care. You are saying I want to store 500 integers. I am saying I want to store 2000 characters. So it's up to you how you want to typecast. If I want to store 500 integers, then I will say int star. If I want to store 2000 characters, then I might also say char star, right, as a typecast, and then left hand side will be a character pointer. So that's how the dynamic memory allocation is working. This anyway, this is important, so let's do this also. As you free a pointer, whatever you are actually doing, it means that this pointer which was pointing to somewhere, let us say 1000, it is pointing to an integer here, and this integer x is at 1000 and it was 27, and you are saying that free p means that p now has nothing. Nothing means p has 0. That is special address which nobody can access, and it actually is equivalent to null. That is what is free p. So p now has 0, means p's, this particular link has been broken. So now if you say star p equal to 5, where will it go? Where will it go? It will have nowhere to go. Right? So this is not allowed because you have freed p. Now if you say that p is equal to malloc of 4, right? So if you say p equal to malloc of 4, then a memory of 4 bytes is given to you. Let us say this is at 1000. This malloc is given to you. Now you do some work here. Let us say you have put here 2379, etc., etc. Again you say p equal to malloc of 4. What will happen? You will get a fresh block of memory. right? Let's say at 2000 you'll get a fresh block of 4 bytes, and this is lost. So be careful when you do a malloc after another malloc, your original memory gets changed, right? You are getting a fresh memory. Every time you do a malloc, you'll get a fresh memory, your old memory is gone. And if you do free 2 times, then the second time it will crash. Free P, fine. I had a pointer which was pointing to 1000. So free P means that this will become blank. After that, if I do one more free P, then P doesn't have anything. So putting another, when P doesn't have anything, if you are trying to free it, that means you are again trying to put a 0 on a pointer variable which is now pointing to a restricted area. So this will result into a crash. So this is what the common pointer pitfalls is. And with that, we come to the end of the first part of this lecture. And I hope you are, I'm not seeing any chat discussions. I hope you are getting clearer in terms of what we are trying to say. But then the next set of things will be a short round of recursion, and then we get to the most important topic of DSA, which is structures. So be with me. We'll come back after 15 minutes. I'll put a timer on here, and when this timer reaches 0, we'll start the session again. Okay, let's start off after the break. Let's quickly complete what we have to complete, because these two topics are very important from your DSA series standpoint: recursion and structures. And of course, I'll use structures to help you get into linked list, and that's where we will end the session. But then before we go there, first of all, we need to understand, for people who don't know about recursion or feel difficulty in understanding recursion, I'm trying to make it easier for you. Let's say we want to find out the factorial of a number, which is 5 factorial. Now, if we have to find out 5 factorial, then we have a factorial routine here that you can see on the left side. And this is an iterative routine which goes from 1 to n and does what? It actually says that result equal to result star equal to I. So what does it mean? It means that your result, if I track result along with your I, right, then I will get that at the value of I equal to 1, the value of result is 1 multiplied by 1, because result's original value was 1. So this is 1 multiplied by this I, which is 1. Then I moves on, I goes to 2, and the result becomes whatever is the result. What is the result from the previous instance? It is 1. 1 multiplied by 2, that is my result. Then I moves on to 3. When I moves on to 3, your result is 2. So this is 2, right? So 2 multiplied by 3. And then what happens is I moves on to 4. So this is 6 multiplied by 4. I moves on to 5. And this is less than equal to n. And I'm saying 5 factorial. So my n is 5. So my n is equal to 5. Right? So this will actually run and say that 24 into 5. So if you see this output, this will be 120 as the output. But then what did we achieve in terms of the factorial? We have done 1 into, 2 into, 3 into, 4 into, 5. When we went down this ladder, we actually multiplied 1 into 2 into 3 into 4 into 5, and we kept on storing the individual stages in order to get to that final 120. Now, can I write this as 5 into 4 into 3 into 2 into 5, 2 into 1? Just reversing it. Multiplication is commutative. I just reversed it. So what have we actually done is really this. Now, can I say that this is 5 multiplied by 4 factorial? Right? So this is actually 4 factorial. Na? This is 4 factorial. So 5 factorial can be written as 5 factorial is equal to 5 into 4 factorial. If I want to do 4 factorial, I can write this as 4 into 3 factorial. Just the same logic. If I want to do 3 factorial, then I will write 3 into 2 factorial. If I want to do 2 factorial, I'll write 2 into 1 factorial. If I want to do 1 factorial, I'll write it as 0. Sorry, 1 into 0 factorial, which is going to be 1. 1 into 0 factorial, which is going to be 1. And then you can do a 0 factorial, which anyway is 1. Right? So that's what you will be doing. If I interpret this in that way, that this is 5 factorial, 4 factorial, 3 factorial, 2 factorial, and every time, what am I doing? I'm shrinking the problem. See, your problem was 5 factorial. As you go down, you are shrinking the problem. Right? So you're shrinking the problem by saying, I don't need to do 5 factorial, let me do 4 factorial. So 4 factorial, 3 factorial, you're bringing down the problem size. Right? And what you are doing is, you are repeatedly doing a factorial at every stage. You are repeatedly doing a factorial. So shrinking down the problem plus repeating the original step. Repeating the original sub-problem. That is what you are doing. When such a thing happens, along with one more thing, that is this last stage, where at 0 factorial, you know that you will return 1. The rest of the factorials you said, I don't know what is it. 5 factorial you said, I don't know what is 5 factorial. I know 5 multiplied by 4 factorial. You could not give the answer. So you said 5 into 4 factorial. You never get the answer. 4 factorial said, I cannot give the answer. 4 into 3 factorial. 3 factorial says, I cannot give the answer. 3 into 2 factorial, and so on and so forth. But 0 factorial gave the answer. This is the only one which has given you the answer. So this is the only one that will give you the answer. And this is therefore called as the base condition. If you see shrinking nature of the problem, repeating the original problem and a base condition, then it qualifies for you to write the program as a recursion program and not an iterative program the way I have written it here. And not an iterative program the way I have written it here. So you need to see whether the problem is shrinking every time you are doing the same job, repeating the same sub-problem, but in a smaller manner. Earlier it was 4, now 3, now 2, smaller manner. And then finally you know the answer. That is the base condition. So if these 3 satisfy, you are in the right track of doing recursion. So if we do recursion, this is how the factorial program will look like. If we do recursion, that factorial, this is my base condition where I'm saying that if it is equal to 0, I will return 1. Else for everything, what am I doing? Every time I am doing what is the function input multiplied by again calling a function which does factorial. So if you see what we are doing here, we are actually saying that we will, let me utilize this part of the screen 1 minute. So if you see what we are doing here, we are actually saying that I want to see a person who can do factorial. So this is a person who can do factorial of 5. This is a person who can do factorial of 4. This is a person who can do a factorial of 3. This is a person who can do a factorial of 2. This is a person who can do a factorial of 1. Right? So what am I saying here is, and then this is a function which can do a factorial of 0. So what am I saying here is, this person, when from main I ask that what is the factorial of 5, I ask this person what is the function of factorial of 5, and this function, this particular person says that I don't know the exact factorial of 5. I know that it will be 5 multiplied by factorial of 4. That is what this person says, that he doesn't know, and he says that 5 multiplied by factorial 4. So immediately when you do that, this goes here to the next person, and this person's job is still pending, right? Here it starts a pending state because it was supposed to return the 5 factorial. It could not. It says that, hold on, I know it is 5 multiplied by fact 4, so let me give it to the fact 4 guy, and hold on, I am still pending. I will give you the response, hold on, right? So it goes to fact 4, and inside of fact 4 it says that fact 4 will say now that I don't know what is 4 factorial, but I know that I need to keep 4 aside and call fact 3 guy. Fact 3 guy will help calculate fact 3. But because you have asked me, I have a responsibility. I will give you back, so I will also be in a pending state. Right? Next, what comes is that this fact 3 guy says that I know that I have to do 3 star. I don't know what is fact 2. I have to call somebody else, the fact 2 guy. Right? But because you have asked me, I will keep myself in a pending state. Now when I go into this fact 2, I will say that this will be 2 star fact of 1, right? Because it says that I don't know what is fact of 1. So I will take the help of somebody. But because you asked me, I will keep you in a pending state. I will get the response and I'll come back to you. So it calls this fact 1. And the fact 1 says that I know that this will be 1 star fact of 0, but I still don't know what is fact of 0. I need help from someone else, and when he gives me the response, I will come back to you. So this keeps it in a pending state. This guy calls this. Now this guy says, hey, this guy says that I know what is fact of 0. The fact of 0 is 1. So let me return 1, right? And then this person gets this return, right? So let me return this, and this person gets the return, means this person now can move on from the pending state to the state where it can calculate 1 star 1 and return it here, right? So this person now can calculate 2 star 1 because this is what is coming from there. So this is the thing that is coming from here, right? So the 2 star 1 is what it calculates, and that is what it returns. This is getting returned. So when this gets returned, it will calculate 3 star, because this 3 is here and this return is here, which is 3 star 2. So this will now get returned here. So this will be 4 star of 6, right? And this 4 comes from here, this 6 comes from here. So now this can go here, and then this will say 5 star of 24. So this 5 comes from here, this 24 comes from here. This 24, 5 star 24 goes back to main, and main then prints that this is the factorial, or whatever that answer variable, or whatever variable you would have taken inside of main, which is going to print your 120. This is what happens when you do recursion. So you actually have small laborers, right, which will do the same job but in a smaller fashion. And then suddenly there will be one laborer who will know the answer, where it will stop, and all the laborers who are waiting will now have their results. That is what is recursion for you. So if I just take this and draw something which is called as the lifeline diagram of the function, so it looks like this. So when I say main, now main actually does what? Main actually does just one work. Main prints f what is the factorial of 5. So basically it calls factorial of 5, right? It will do a print, that is fine. So internally what it does is it will call factorial of 5, and then it will also need to do what? A printf. Now I will keep it here just so that we don't lose track of it. Later I will move it, right? So hold on with that thought. We will move it later on. Or rather, let me write that printf is still pending for main here. Let me not use this space. Now what is this line that I have drawn? This line that I have drawn is the lifeline of main. Till what point does main stay alive? Till what point that this bracket does not hit? Right? As soon as this bracket hits, main is over. So this is where this bracket will hit. That's my assumption, right? So let us do what all main is supposed to do. So main is supposed to do factorial of 5, right? So factorial of 5 is what main is supposed to do. So when you do this, this particular factorial will come alive, right? It will take birth. This particular person will start to work, right? So I'm saying this particular person's lifeline will start. So this person, as I know, if you see every person who is supposed to do factorial does two things. They do two things. The first thing they do is they check for the base condition. They check for the base condition. This is what the base condition that they check, right? So this base condition is what they check. And then they do what? N star factorial n minus 1. They return n star factorial n minus 1. These are the two things that they do. They return n star factorial n minus 1. These are the two things that they do. So what will factorial 5 do? The factorial 5 will do these two things. So factorial 5 will first do the base condition check, which will return false, because 5 is not equal to 0. N is 5. 5 is not equal to 0. So it will therefore return what? It will return n star factorial n minus 1 means 5 star factorial of 4. It will return this, right? But when immediately you do this, what happens is this factorial lifeline will start, and this guy is waiting. This guy has not got this response, so this lifeline still continues. right? It cannot end because the job is not over. The job is still in a pending state. But a new person is now engaged who will do factorial of 4. Right? So the factorial of 4 guy will do 2 things again. As you know, each factorial guy does these 2 things. So this will do factorial of, this will do a base condition check, which will become false, and it will do a return of what? It will do a return of, because it was called with 4 into factorial of 3. As soon as this happens, this particular person will come alive. Right? And this particular person will say that I want to do the base condition check first, which will be false because it is again 3, and then I will do a 3 star fact of 2. As soon as I do that, this particular person will come alive, and they will say that I need to do 2 things: base condition check, and this will be false, and then I need to do 2 star fact of 1. And then this fact of 1 will create a new person which will come alive, and it will try to do fact of 1. And in this fact of 1, it will again say that I need to do 2 things. That is, I need to do a base condition check, which will be false, and I need to do a 1 star fact of 0. So fact of 0 will come alive, and fact of 0 will say that I need to do a base condition check. And as soon as it does a base condition check, it will become true. As soon as it becomes true, it will return what? It will return 1. This is the return 1 that will go out. Right? As soon as this return 1 goes out, it will come here. Right? So this return 1 will come here. And therefore, this particular, once this return 1 goes, this job of this particular fact 0 is over. So this lifeline will terminate. This fact 0 job is over. So this lifeline will terminate. Right? And then this return 1 will be actually used to calculate 1 star whatever is coming out. Right? So this will be a 1 star, the return that came from this side. So 1 star 1, this will be returned here. And because this job is over, so this will also terminate. Right? Now this 1 star 1 comes here. So the return that this will give will be 2 star, the result of this 1 star 1. So this will go to the left, and this is how it will go on. So this will be over. So this will be 3 star 2, and this will get over. This will be returned here. So this is going to be 4 star 6. This will be returned here. This will be 24 star 5. Put it like this. And this will be returned here. And when it does, it will cross. This will be returned here as 120, and that print of 120 will happen here. So now this 120 once it is returned, remember we had held this printf. Now this printf will now go here. So we will now have a printf of 120, and that 120 after it is done, the main lifeline will close. This is how the entire stack or the entire stack winding and unwinding is happening with respect to a recursive call. Any recursive call will go through this. This is how your object lifeline or function lifeline will actually work out. Right? People will wait, and then finally it will get the data. At that point it will close its whatever is the work that it was supposed to do. So that was recursion. This is all that we need to understand. Any recursive program, if you have understood, that's enough to get into DSA. So from a structure standpoint, last topic that we are starting, just to understand what is a structure. Every DSA problem will start with a structure. Every DSA problem. So you have to understand what is a structure as far as DSA is concerned. So let's understand what is the necessity of structure and then we will get on to the nitty-gritties of it. Now if I say that I have a roll number which is 3, an array of roll number which is 3, so then this array will look like this. So 103, 101, 102, and this is what is called as roll, right? So this is my roll number array. I have a character array which is a 2-dimensional array with 20 pockets to hold names, right? So if I have a character array with 20 pockets to hold names, it may look like this. Now assume that there are 20 pockets, 20 lines, in fact 19 lines that I am drawing here. So let's say this is 20, and this is my 3 pockets, and inside this I have Aman, /0, Riya, /0, Karan, /0, right? So you have Karan, I just misspelled this, yeah. So let's say this is how it is, and then you have a float marks which is also an array of 3. So this is, and these are your 3 pockets. Something is 89 point on roll number, right? If I write a function called sort on roll number, what will happen is that this function is supposed to sort the roll number. Imagine that the roll, the name, and the marks are tightly coupled with each other. That is, roll number 103 is Aman, who got 89.5. Don't you think that is what this data represents? Aman is of roll number 103 who got 89.5. Karan is of roll number 102 who got 76.3. That is what this number, this entire thing represents. But does this array know that it has to go hand in hand with this array? Does this array know it has to go hand in hand with this array? It doesn't. So when I sort roll number, it has no clue that there is an array called Aman which also it needs to sort. There is an array called marks which also it needs to sort. So if I sort this roll number in an order, so 103, 101, 102, I want to sort it in ascending order. So I want this roll number to become like this. So roll number now becomes 101, 102, 103. So against this roll number 101, that is at the 0th index, 1th index, and 2th index, what do you think has happened to these 2 arrays? After the sort, what do you think has happened to these 2 arrays? They have not changed. They have not been sorted. So if I now say that, tell me what is roll number, let's say roll number at an index of 1, what is the marks of this person? If I say what is the name of this person, then what will you do? You will say that, okay, I will go and print the name array at 1 because this is roll number 1. So I will print it for the name array at roll number 1. And this will come out as what? This will come out as Riya. Is roll number 1 Riya or roll of 1? What is roll of 1, by the way? Roll of 1 is 102. So this is my roll of 1. This was 102. Where was 102? 102 was for Karan. What was Karan's mark? 76.3. Now when I say roll number 100, roll number 1, it means 102 roll number. What is the name coming out to be? Name 1, right? Name 1 is coming out to be Riya. Why will I change roll 1? When I say roll 1, I will never assume that name has to be 2, na? Because whatever index is in roll, the same index needs to be applied in name. Right? So if I understand this, that roll and name go hand in hand, what about marks? What will be marks? Marks will also be marks of 1. What is marks of 1? Marks of 1 is 91. Whose marks was it? It was Riya's mark. It was not Karan's mark. Karan's mark was 76.3. So I was supposed to get 76.3. I got 91. So this I was supposed to get Karan. I got Riya. That is the problem. When you are having multiple data to be stored, but all these data represent a single entity, storing it in different variables creates a problem. That they are not interrelated. Any operation on one variable is not visible to the other variables. So the other variable and this variable are not in sync. And that is what the problem is creating. So I hope you have understood this problem. And from this standpoint, if I move on, then you will understand that this can be easily solved by getting into a scenario what we call as structure. So instead of keeping all these three variables outside, let's package them inside. Right? Let's package them inside. If int x is a variable, x is a variable of data type, this means that x is a variable of data type int. So can I say roll, marks, name is a variable of data type student? If that is done, then we are done. I have created a separate data type called student, and inside this student I am saying that this is a data type, and inside this data type I have three different smaller data types, right? Int, marks, char, name, and then what do we have? Int, roll. These are the smaller data types that I have. So student is actually, if you think about it, it's a data type at the end of the day, right? You will be creating the data for the student. Data for student means that you are creating data for a data type. Both of them are the same, right? When I say int x equal to 10, this 10 is the data for int. Similarly, you will create data for student, right? So you are going to create data for the student means you are going to populate inside this. All these three will be together because now they represent one single data type, right? All this while you knew that data type contains only one type of variable: integer, character, float, long. Now we are saying that the data type can contain multiple variables. These multiple variables represent that entity that data type represents. Student. Student is not just an integer. It is an integer which represents marks, character which represents its name, and integer which represents its roll number. So why not put them together inside a package called as student and name this as a new data type? That is what is structure. Right? That is how you define a structure now. So struct student, int roll, name, marks. You have created your own data type. If you have created your own data type, right? If you have created your own data type, just like you do int x, can you do student s? Can you do student s1? Again, data type, variable name. Data type, variable name. For structure, because student is a structure, you just need to put the struct keyword before it, and we will remove this struct keyword in the next slide. You will see it will exactly represent the data type, the way you do data types. So now you have created a variable called s1, and while creation you are initializing it to say this is my roll number, this is my name, and this is my marks for this particular student. So S1 gets created in memory. So S1 gets created in memory with the roll number block saying 103, with the name block saying Aman, and with the marks block saying 89.5. This is your S1. S2 block here gets created. Next, these are variables. The way you create variables on RAM, same way you are creating this. Only thing is you have to just remember that this is no more a single block variable. It is 3 blocks because there are 3 data types inside this variable. So S2 now becomes 101, RIA 91.0, and S3 now becomes 102, Karan, and 76.3. So this is what is happening with the program on the left. So I hope you have understood that we now have created our own data type. Our data type is a combination of multiple data types inside it. And because we have created our own data type, the way you do it with native data types, defining a variable, the same way we will do it with our own data types. Define a variable like this. After that, we will have to use this variable the same way as we use this variable. There is no difference. So let's see that before we go on. So just that before we go on to that area, I told you, right, we have defined our own data type. So if I can write int x equal to 20, right, as for x as a variable for a data type called int, then for my student, why can't I write student s1? Why do I need to have struct written in front of it? Right? So let's eliminate struct. For that, all that you need to do is use this type def keyword. You are defining a type. Type def means defining a type. Now you are telling the compiler that you just don't have int, char, float, long, etc. You now have another data type that I have created, which is called as student. This is a new data type you have. Through this type def, you are defining this to the compiler. That along with these type, this is also a type. That's what you are telling the compiler. So the compiler will now be happy if you say just student s1. You don't need to put the keyword struct in front of it because you have defined it as a valid data type. Right? So that's what is type def. Now accessing the structure members, just now that we have defined the variable, we also need to access it. So the access is through the dot operator. So if I have defined a student data type s1, then s1 resides in RAM like this. That s1, it will also have an address 1000. Right? Inside this, there will be a roll number area. That roll number area is having 103. There is a name area. The name area is having Aman. There is a marks area. The marks area is having 89.5. So if I have to access the roll number, I will say s1 then dot roll. See, earlier if I have to access int x, let's say 23, if I have to now access x, I just say printf %d x. The reason for that is this x, right, is this, right? So if I say 23 here, this is my x and this is at, let's say, 1024. So if I say x, it knows that it can go into 1024 and get into x, right? Get into the value of x. But when I say s1 printf %d s1, if I say printf %d s1, what would it mean? It would mean go to 1000. Okay, fine, I went to 1000, but where? What will I do inside 1000? There are so many data types inside 1000. Right now we have 3. There could be a structure where it could be 100 data types inside it. Right? What do we print out of this? We print 103, Aman 89.5. Then why? How will we print to through %d? We will have to give that many number of format specifiers. So it doesn't allow you to print the entire structure like this. Here there was only a single element, %d is okay. But this is a variable which has multiple data inside it. You cannot use just vanilla %d with s1. If you have to use %d, then use it with the integer variables inside s1. So say s1 dot roll. You will say s1 dot roll, or you will say printf %s s1 dot name, or you will say printf %d s1 dot marks. Right? So this is what you will say when you are actually trying to access the structure elements from a from a dot operator standpoint. You'll use the dot operator to access the structure elements, and you'll use them to actually get into the structure and print this. What is happening behind the scenes? If you see, when I say S1 dot roll, right, so it will use this S1 as the base address, which is 1000, and it knows that roll is at 1000. Aman is at 1004. Why? Because this is 103 is an integer, right? So if it is an integer, it is supposed to take 4 bytes of memory. So this is actually 4 bytes of memory. This is 20 bytes of memory because you defined the character as 20 bytes. If you see here, the structure was defined as 20 bytes for character, right? So this is the area where you defined it. And now if you come out here and say that, so Aman is 20 bytes. So now I know that this 89.5, that is marks, will start from 1004 plus 20, which is 1024. So when I say S1.roll, it just says that S1.roll is at 1000. So go to 1000 and print whatever is the value at 1000. So you get 103. But if I say S1.name, then it says that S1 is 1000, okay, and name is 4 offset ahead of 1000, or rather I would say 1 offset ahead of 1000, which translates to 4 bytes, right? So S1.name is actually 4 bytes ahead, which means it is 1004. How does it know it? Because int comes before in the structure definition, so it has defined int at 1000. Int takes 4 bytes, so the name starts from 1004. So when you say S1.name, it knows that it has to go to 1004 to extract that name. So when it goes here, it will get Aman. And likewise, when you say S1.marks, it will take your base address, which is 1000, and it will add 4 bytes, and it will add 20 bytes because it has to skip the integer portion, it has to skip the character portion and go to the marks portion. So this gets to 1024, and from there it will get 89.5. So this is how your dot operator is working, right? So I hope now you have a proper understanding of this. Now the dot operator can work either ways. You can say that S1.marks printf, which is the read operation, right? So these are all read operations. Or you can say S1.marks is equal to 100. Now this becomes a write operation. It is just the same as any other variable. So as soon as you get to one variable inside it, the treatment of variables will remain the same. All these are the lowest variable, that you cannot go beyond roll, you cannot go beyond name, you cannot go beyond marks, right? So these are the lowest variable inside it. So when it is the lowest variable, when you have reached the lowest variable, the treatment of that variable with respect to read-write operations will remain the same, right? So the treatment of the variable will remain the same, means this will be used for read the way you use it with x, right, for read. Similarly, S1.marks equal to 100 is the same way. So imagine this to be the entire variable name, then it will be easier for you to correlate. This is the entire variable name, right side is the variable value which will be put inside the variable name. So that is how you access the structure element. Array of structures, very important. We have to understand this. Now the array of structures would mean that I have defined, I am saying that I will create three array of student class, right? The student class, we know it is an integer, a name and a marks. And I'm saying I'm going to, instead of creating 3 variables or 1 variable, I want to create an array, right? So I'm saying I will create an array like this, right, of these 3 structures, of this 3 structure variables added together as an array. So let me use this like this, right? So this is my what is the name? We have called it as a class. So I'll call it as a class, right? So I have told you that a name of an array is a pointer, right? Name of the array is the starting address of the array. So if this is a structure student, right? So if this is a structure student, this is also a structure student, this is also a structure student, right? So all three are student structures, and inside this student structure, you have these three areas. One area is for your roll number, one area is for your name, and one area is for your marks. Here you have 101, Ria, and 91. Here you have 102, Karan, and 76.3. Right? So I just now told you that my name of the array is the starting address of the array. So if this is an array starting at 1000, don't you think this will take 4 bytes? This will take 20 bytes. This will take how much? 4 bytes more. So how much is the total bytes that I am taking? 28 bytes. So 28 bytes for this entire structure. So where do you think this will start? So this should start from 1028. Right? So this should start from 1028. This will also take 4 bytes, 20 bytes, 4 bytes, total 28 bytes. So 1028 plus 28 is 1056. So this will start from 1056. This will also take 4 bytes, 20 bytes, and 4 bytes, 28 bytes. Right? So this is how the array will look. This is how the memory will look. Right? And I told you that the name of the array is a pointer which holds the starting address of the array. So this will be pointing here. This is how the entire array of structure for the left hand side will look like. And now if you see, I have said class 1 name. Class 1 name. What does that mean? It means this. Pay close attention to this. It means, you know, class 1 name means class plus 1 star dot name. By now you know this. Refer to the array discussion that we did just now. It means this, right? You can interpret it as in a different way also. You can say this is 0, this is 1, this is 2. So class 1 represents this student. You can of course do that. I'm just trying to show you the difficult part of it, how you realize it, so that this question, if it comes, you understand what is happening. Right? Class 1 name is, go to the 1th pocket and get the name. Ria will be the answer. So I hope you understand that this will be Ria. Right? But then what happens? Let's see what happens behind the scene. Right? So what happens behind the scene is that this class 1 name is star class plus 1 name, because I told you that the base address is the starting address, which is 1000 plus 1 block. 1 block here means what? 28 bytes. Right? So now it goes into star of this. Right? Star of this. Now the star of this means go to that address, which is 1028, and in that go to name. Right? So this becomes 1028 dot name. And did I tell you that if it is name, it understands that 1028, it has to skip 4 bytes because int is ahead of the name. So it will go to 1032 and it will extract the value because it has a star ahead of it. So it is star of 1032, which will extract Ria. So if you see here, 1028 plus 4 bytes means Ria is at 1032. Right? So this is how your structure behaves when you actually put it inside an array. And this is how we will be using the structure as an array. The structure is an entity which has multiple elements. There can be so many entities. Human being is a entity. It has let's say color of eyes, color of hair, etc., etc. Those are your attributes inside that structure. Those are the integers inside that structure. And there can be so many human beings. That means the data type you created called human beings, now you create an array of that data type. And that's what we have done. Why that array behaves like this, why class name, class 1 of name translates to Ria, is what I have tried to explain using pointers. So I hope you have understood the array of structure concept. So now on this next thread, that is on this particular topic after array of structures, we also need to understand that if you do something like this, that you have created a structure called S1, you are calling this as S1, and inside of S1 you have 103, you have Aman, and you have 89.5, right? It does, and you create one more structure which is a blank structure, S2, and then you say S2 equal to S1. S1 is at 1000, S2 is at 2000, right? And therefore when you say S2 equal to S1, it will piecewise copy all the elements into the new structure. So this will contain 103, this will contain Aman, and this will contain 89.5. So S2 equal to S1 will be this, and this would also mean that if you do S2.roll and want to change it to 999, right? If you want to change S2.roll to 999, then S2's dot roll will be changed to 999, will have no reflection on S1. So S1.roll is still at 103. Similar to creating a new variable and changing it so that the original variable doesn't get changed, same concept, right? So I hope this part you have understood, that when we copy a structure, it actually has nothing to do with the original structure. A carbon copy gets created. Now if that is the case, then can we compare two structures also? We can copy two structures by saying S1 equal to S2. But can we say S2 equal to S1? Can we compare them? When I compare them, it has to go inside and compare all the individual values. Otherwise, there is no point of comparison of structures, and it is difficult for it to do that. That's why it has been kept out of C, that no, I will not do any comparison. If somebody has to do comparison, then they will have to say that S2.roll should be equal to S1.roll, and S2.marks should be equal to S1.marks, and S2.name should be the same, which where we will, because of name we have to use strcmp S1.name, right? So this should be equal to 0. The comparison should return 0. If we can do this, then only we can say that the structures are equal. So we cannot directly compare, while we understand this is a variable, this is a variable, two variables are equal, right? So we cannot directly compare the variables because these are complex variables. These are not simple variables. So that's why we cannot compare the two variables like this. We will have to go inside and compare the variables, right? So we'll have to go inside, compare all the individual variables to make sure that all the individual three variables, at least as far as this example is concerned, is compared. So that's where I hope you can now compare this. Now what happens if we pass a variable to a function? In C, all variables are passed by value, right? So if I pass a structure variable to a bump function, right? If you see here, the bump function is actually accepting the variable inside this struct student variable, right? If you have done the type def, you don't need this. You can just do student s. But let's say that from main I am doing something like this, bump s1, and s1 is a structure variable for students. So I have written that here, let's assume that, and then I am doing this. So then what happens? This s1, definitely you would have done something like this, struct student s1 equal to something, you would have written 103 Aman and then 87.2, right? So this is what you would have done to define struct s1 and initialized it also, and then you are saying bump s1. What is happening is main will have its own set of memory. So this is main's memory, this is main's memory, and inside main's memory, main says that I want a structure variable s1. So it has an address of 1000. Inside that you have given spaces for storing 103, Aman and 87.2. Right? So main's memory has 1000 as a structure starting address, right? From where you get into roll number, you get to name, and you get into marks. And then you will also have the requirement of the bump, which says I need a S variable, a structure variable called as S, a structure variable called as S, and this is my bump function. And inside that bump function, what will happen is this entire content will get copied. This entire content will get copied means 103 will go there, Aman will go there, and 87.2 will go there. So when I say bump S1, S1 gets copied into S. S1 here, entire thing gets copied as a value. So copied or carbon copy, copy as value. Or I will say carbon copy. Same as in pass by value. Right? Like X, if you pass to a function, it is copied exactly and nothing happens to the original X. Here also, nothing will happen here. Even if you, from bump, if you say S dot roll is equal to let's say 104. If you say that, right, so this will become 104. This will become 104. Nothing will happen to this. This will still stay at 103 because main is not touched, right? Because you have copied the structure variable from main. So this variable gets copied from here to here. So nothing, any changes here will not impact here because it's a copy, right? So that's the structure passed by value. Now, if you are inside a function, how do you send a structure out of the function? So if I have a make topper function, which creates a structure, student S, right? And in that it says 101, then RIA, then it says 91.0, right? And then it wants to return this S. What happens when I say from main, if I say that I want a structure student best, which will be equal to make topper. Now remember, make topper returns a function structure. So the return type of make topper should be struct student. You can eliminate this if you have done a type def, but the return type of make topper should be then student because it returns that new data type, right? And that new data type is getting stored here. So when you return this inside of make topper area, inside of the make topper area of memory, what is happening is make topper is creating a struct S, right, which is actually having 101 RIA and 91.0, right? And then when you say return this, then this will be returned as a copy again to main, right? Which means that inside of main, the best variable that you have defined here would create a copy here. So there is a carbon copy getting created here again, and this carbon copy is going to have 101 RIA and 91.0, right? So this best variable has now nothing to do with this S. If I change best dot roll to let's say 27, then this will change to 27. This will still be 101. Actually, this is anyway dead because this function has anyway returned from here. So this variable area will no more be accessible. But the concept is that a carbon copy gets returned. The original variable that is there inside gets lost. Right? So this is a typical interview question that can be asked, that we all know that inside a function a variable gets lost when it gets created, or when it gets when the function actually gets executed and is completed, right? Then how can you return something from the function, right? The way we are returning from the function is we are not returning that variable, we are copying its values to main's location, right? So we are not returning. If we would have returned this address, then that would have been a problem. I'm not returning this address, because this address will have no existence once the make topper is gone. That is why intelligently I am putting all of this inside main's address, because main will now take over. So main, let it be happy with that. I anyway am going to go dead. So let main be happy. So this is a very important interview question. That's why I kept it here. Now structure sizing and padding, if you see, this is also important. Let's say that we have a roll number. Now when memory gets allocated, typically it is allocated in terms of the microprocessor architecture and the operating system architecture, in terms of how many blocks of memory can you allocate. Can I just allocate one block of memory? Right? So can I allocate let's say 1 byte of memory? If the next byte is asked, will I go to the immediately next position and search? So what I'm trying to say is, if there is a RAM like this, and if these are the memory areas, and I have been asked to give you let's say 4 bytes of memory, right? So then 4 bytes would be in this and this, 4 bytes of memory, and then I'm asked to give 4 more bytes of memory. So then I will be not able to give you 4 more bytes of memory, because there are only 2 bytes of memory in this space. So I'll not be able to give you 4 bytes of memory. So net, what the RAM and the compiler tries to do is, it tries to optimize the memory allocation to a max of 4 blocks. And 4 blocks I'm taking because of the modern architectures. It could be different for different operating systems. I'm just taking it from a lecture standpoint to 4 blocks. That 4 bytes of memory, or 4 blocks, I would not say, it's 4 bytes of memory. So 4 bytes of memory is actually allocated, or is actually spared to be allocated at every point in time. I'll help you to understand this. Let us say that roll number is 4 bytes, right? We know roll number will take 4 bytes. We know name will take 20 bytes, because there are 20 characters that we have to store. And we know that marks will take 4 bytes. So when I go to the RAM and ask it that I want 4 bytes for roll, I want 20 bytes for name, and I want 4 bytes for marks, then what it does is, it goes into its own area where it checks for free memory, and it says that yes, I have a free memory starting at 9000. I have a free memory starting at 9000. From there, I will allocate 4 bytes. From there, I will allocate 4 bytes for roll. So now I have reached 9004. And from there, I will allocate 20 bytes. Right? So there I will allocate 20 bytes of memory. Now, when I do this, this starting address becomes 9024. Now, is this a multiple of 4? This definitely is a multiple of 4, because it started from 9000 and not really a multiple of flow. What I'm saying is, from this point onwards, am I allocating in multiples of 4? Right? Here I allocated 1 multiple of 4. Here I allocated 4 multiples of 4. Right? And from here I have allocated again 1 multiple of 4. From 9024, I will allocate some 4 bytes of memory again. So every time, every allocation is a multiple of 4, right? As far as this this structure is concerned, right? So for this kind of a allocation, there is no problem. All I'm saying is, whenever the memory is allocated, it is supposed to be allocated in a multiple of 4, right? For easier referencing and easier access to structures and memory. And here, roll, name and marks are in such a sequence that even if you don't do anything, you will always be allocating in a multiple of 4. The first one is a multiple of 4. The second one, 20 bytes, is also a multiple of 4. The 4 bytes that you need is also a multiple of 4. So there is no problem. You have allocated continuous memories in a multiple of 4. Now let's say that we say char a int x char b. If we put this inside the structure, you create a new structure and put it inside that. If we put this inside a structure, so you are wanting 1 character of memory. So even if that character of memory starts at 9000, even if that structure starts at 9000, so the A will want to take 1 byte of memory character, right? So it will take 1 byte of memory. Is this a multiple of 4? No. So which is where it will put 3 bytes of padding. It will unuse that memory, but it will give it for you to use, but you will definitely not use because you are using a character. So you will only be using this block, you will not be using this block, but it gives you that memory. So it actually allocates 4 bytes here, right? So 4 bytes, when I ask for a character, it will actually give me 1 plus 3, so that it gives me 4 bytes. Then I ask for it for an integer. When I ask for it for an integer, it is happy, 4 bytes gets allocated. So this becomes 9004. Now when I ask it for another character B, right? So this is my A, this is my X, and I'm now doing my B, and this B is 1 byte, right? And then 1 byte is not a multiple of 4, it adds 3 more bytes, right, as a padding, and therefore this becomes 4 bytes again. So we have how many bytes? We have 12 bytes of space getting allocated for this particular structure, right? So if I say char A, int X, char B, it is not 6 bytes, because you might think char A, int X, char B is 1 byte, 4 byte, 1 byte, 6 bytes. No, there will be a padding of 3, there will be a padding of 0, there will be a padding of 3, which means it will become 12 bytes. So there is a wastage of 6 bytes of space, right? And if it is like this, that instead of doing it, just rotate or just change the sequence of that same character, int X, char A and char B. If you do this like this, then same 9000 it will start, and here int X means 4 bytes, and it is happy multiple of 4, right? So 1 multiple of 4 is allocated. So you now are at 9004. Inside 9004 you have to allocate 2 characters. When you are allocating 2 same data types, right, back to back, it does not do the padding, because char A, char B comes back to back. Earlier case it was not coming, int was in between. So if you have char A, char B back to back, then it will allocate 1 byte here for char A, and then it will allocate 1 byte here for char B, and then it will pad 2 paddings, so that this entire thing now becomes 4 bytes, right? And this is 1 multiple of 4 byte. So what do you have here? You have 8 bytes of space. So just by changing the sequence of your structure operators or structure variables, you actually achieved reducing the unused space by 4 bytes, right? So I hope you are understanding that if there are the data types are actually the same, then there is no padding in between the data types. After all the same data types are kept, then it will start to pad, so that it becomes a multiple of 4 bytes, right? So that is what the structure size and padding is typically all about. Now coming to the end of this particular topic, some 2-3 subtopics are left, and we will come to the end of this. So let's say now that we know that a structure can contain data types like this: integer data type, character data type, again an integer data type, right? This is what a structure can contain. It's our own data type, right? Now can I create a own data type then containing a pointer? Let us say I will have roll as an integer, and then I will have the score as a pointer. So I will point to a score which is outside the structure's memory space. So if I say this, then this is actually called as, let us say S1 is the name of this structure. So S1 is at 1000 address, right? And inside of S1 I have 2 variables, one roll and one an integer pointer to the score, which we call as the score pointer. So what is happening if I show this in a large manner. Let me blow this up for you. So this is going to be my role, which is at 1000 address. The structure's address is also 1000, and I'm saying that I need one more variable, which is an integer variable called as score pointer. What is the data type of that? Int. How many bytes will it take? 4 bytes. So this is 4 bytes. This is also 4 bytes. Right? So both the variables are 4 bytes. This contains value. This contains address. Address of what? Address of some other variable. Right? So this contains an address of some other variable. So we have said that int score is equal to 91. So then 91 is here, and let us assume this score is at a 2000 address. And then we are saying that s1.roll is equal to 103. So s1.roll is equal to 103. And then we are also saying that s1.score pointer is equal to ampersand of score. s1.score pointer is equal to ampersand of score. So score is here, address of score, which is ampersand of score, is 2000. So this 2000 now goes here. Right? So inside the structure, we are not storing the value, we are storing the address where the value is stored, which is outside the structure. So that is also possible. So how do you then access this particular 91 from inside the structure? Your structure variable is called s1. So s1 dot score pointer, s1 dot score pointer should be equal to what? It should be equal to 2000. So just put a star before it. That means that this 2000 will be doing a star. So we are not interested in 2000. We will go back to the location of 2000 and we will read this value and we will print this value. So printing means that we will be printing 91. So that is what is happening if you store a pointer inside a structure. It's the same concept, same thing, just you have to be careful on the way you write it. Right? So I hope this part also should be clear. And then when we actually get into the pointer which is pointing to another structure, right? So now we are slowly getting into the linked list and the DSA part of it, where we are trying to say that we will now be pointing to another structure, and the structure is, and there are two structures. So we are saying that I will have a student structure, and then the student has an address, and address is also a structure because address has multiple fields. What are the fields? You remember when we started this discussion on structure, we said if an entity has multiple fields, then create your own data type, which is called as a structure. So we are saying address has multiple fields. What are the multiple fields of the address? The multiple fields of the address are, let's say, the name of the city and the pin code of the city. So if I say that there is an address structure, which contains two things. One, a character variable, character array, which is city, let's say 20, and it has an integer pin code. Right? It has an integer pin code. This is my address structure. Okay. Now your student structure, which was earlier there, says that it has an integer role, it has a character array name of 20, and it also has a pointer to this address. So if it has a pointer to this address, that means if somebody has created a variable of this address structure, I will point to that variable. So then I need a pointer to this address, means I will need a star ADDR, let's say. So this is what the student data type has. So I have a pointer to this address. What does it mean? It means that I have created this address A1 variable, saying that this A1 variable represents the above address data type, and it contains what? It contains Mumbai in this 20 character array, and then it contains 4 1 in this integer variable. Now this may not be sufficient for an integer variable. You may have to put a long variable, but I'm not going there, or it may be a wrong pin code also. I'm not going there. I'm just trying to say that assume that this is a number that can be stored inside a pin code. Now when this happens, that Mumbai and pin code is stored inside A1, what is A1's data type? A1's data type is address. What is the address of this particular variable A1 in the RAM? Let us say the address of this variable in the RAM is 1000. Now if I create student S1, right, student S1, and I say that you are my S1 student, and your address or your roll number, let's say the roll number of this student I say is 103. I will say your name is Aman, and then I will say your address is the pointer which points to this particular variable A1. A1's address is what? 1000. So I will store 1000 here instead of the address, right? So I will store 1000 here instead of the address, instead of the value, that is Mumbai and 4,01,000, right? And there I will say that now this 1000 is the address of A1, because I had created a pointer variable here. It can store addresses, so I will store it as an address. So I will store it as an address of A1. So if I store it as an address of A1, then whatever is A1's address will actually go here. Now can I say that S1 dot address, what is S1 dot address? S1 dot address is 1000, right? So if I do a star, the value at S1 dot address, does it have any meaning? It doesn't have any meaning. Why? Because the value at this address is multiple things, so it doesn't have a meaning, right? So I cannot do a star of S1 dot address. So I have to go inside S1 dot address using the arrow operator, and I have to say S1 dot address arrow pin code, and that is where your arrow operator now comes into the scenario. That this is the reason why you will use an arrow operator. If there is a pointer inside a structure, right, which is pointing to another structure, not a variable. The variable pointing is easy. We have done it here, right? The structure, inside the structure there is a pointer which points to a variable. There you can use star, because go to that address, you will get only one value. So star is allowed, value at that address. But here if you do star, you will get multiple values, Mumbai and 4,01,000. You are not allowed to do this. Multiple values, I said earlier also, you cannot dereference multiple values, or you cannot print multiple values, right? So you need the arrow to point to a particular this one. So dot is used for pointing or getting inside. This is an inside operator for variable, and arrow is an inside operator for pointers. So if you are trying to go inside a variable has multiple variables, I want to go inside that, use dot. But a variable is pointing to a pointer, okay? Now inside that pointer there could be multiple variables. Wherever the pointer is pointing, there could be multiple variables. Here the pointer is pointing here, there are multiple variables. So how do you use this pointer to go inside that? Again, you use the inside operator for the pointer, which is an arrow. So that is why this arrow is important here, right? So this is how we are talking about a structure in terms of another structure, right? Structure pointing to another structure. Now comes the fun part. Now comes the data structure introduction slide, right? And these are only 2 more slides before we wrap up this session. As I said, we'll finish by 8:30. It should be done by 8:30, right? So another maximum 20 minutes we should be done. So, but listen to this part, because all this while we have done this to get into data structures, and this is where we are getting into data structures. Now, if you see an array, and you see that this array is holding data like this, and you want to actually insert an element inside this array. You want this to look like this. You want it to look like this: 78, 29, 30, 50, 70, and 90 is inserted. Now, what do you need to do? You cannot change the size of an array, right? So first of all, you have to delete your original array. Let it go. Create a new array with 1 size extra. Copy all these elements from your old array into the new array and destroy the old array. That's what you need to do. And that is a headache. So it's not a sign of a good data structure. Addition, deletion, subtraction, right? Addition, deletion, updation, traversal, all of this, search, all of this should be easy in a data collection like an array, let's say. If it is easy, all of these functionalities are easy here? No. Is it easy here? No. Which means you need a different data structure to store data which is of similar data types. Like array is a similar data type. An array of structure is also a similar data type, right? So if you have to store the data of an array of structures data, do you use arrays? No, because this is difficult. These 5 things are difficult, so we will not use array. So what we will do is, we will say that I will create a structure, I will store that structure variable here, and inside the structure variable, let's say I have only one integer, right? 78 to be stored, right? So I will store 78 here, and the next variable will be 29 for me. Now where is this variable created? I don't care. This could be created at 1000, this could be created at 2000. There is no sequence between these 2 variables. I am asking the compiler, give me anywhere you want to give me this variable. So this 29 gets created anywhere, 29 inside this structure. By the way, this structure, let us call it as the node structure. Typically, we'll call this as node in DSA terminologies, but you can call it anything as far as the business problem is concerned. I'm calling it as node. Let us call this structure as node. So what is this structure containing? If you see, the node structure is going to contain these 2 things. One is the data. So this is my data, right? The data is an integer, okay? Can I have multiple data types here? Integer data, char name, integer marks. Yes, possible. We are just simplifying things and showing only one data type inside it. You can have multiple data types, but then there is one important data type that you need. If you remember, when I am at 78, I can easily go to 29 if it is an array. Why? Pointer arithmetic, right? So if I know the address of this, as 5000, I can immediately do 5000 plus 1 and then do a star, pointer arithmetic, right, to reach to my 29. So how do I reach from 78 to 29 if I do it like this? Like this in a structure, I've created 2 different structure variables, right? I have created a node n1 structure variable, a node n2 structure variable. N1 is at an address of 1000, N2 is at address of 2000. But how from N1? From N1 I have to go to N2. I could do it in an array very easily. If I knew the address of N1, I could go to the next index, which is N2. But here, how do I know? So that means this particular person needs to know the address of N2 so that it could go inside N2. When it goes inside N2, it can get 29. So this particular person needs to know the address of the next person in the queue, next person in the line, right? So it will store what? It will store 2000. And what is that? That is the address of what? Address of a node, right? So it is an address of a node. So it is node star ADDR. So isn't it self-referencing itself? This is a node, right, which is referring to another node. This is called self-referential structures. This is a node which is referring to another node, right? So here also it will become a node. Another node N3 can come in, right? You can create N3 which will have 30, and this 30 will have what? This 30 will have an address of, let's say, 3000. Then here there will be 3000 here, right? So now we have established a link like this and a link like this, right? So now this can be 4000 because we can have another structure getting 4000 as the address. This will be 90, and let us say this is N4. So this link is also created. So if I am in node N1, can I use navigation to go into, can I say N1 dot, what is it called? It is called next, right? If you see, it is called next. What is N1 dot next? That is equal to 2000, right? N1 dot next is 2000, right? So if I am inside N1 dot next, right, now can I say N1 dot next arrow data? What is that? Next is a pointer, right? 2000 pointing to what? Pointing to a structure which is this at 2000. This is 29, right? So the date, this is my data. So N1 dot next arrow data, I told you, right? Pointer, inside the pointer if you go, right, you have to use the arrow syntax. So N1 dot next arrow data would mean it is 29. If I do N1 dot next arrow next, then what is that? That is 3000. This one, N1 dot next is 2000, arrow next is go to 2000 and go inside and go to next, which is again 3000. So can I therefore say N1 dot next arrow data? Then that will become equal to what? 30. So in this way I can go on and on and on, and we can actually link things together, which we created separately as structures. We can link them together, hence linked list, right? So this is a classical linked list, and if this is the last position of the linked list, then there is no address later on. I will put it as null. If you remember, I explained that pointer, don't keep it uninitialized, put it as null. It will get an address of 0, which is a reserved address. So it knows that till null it will go, and it will keep on doing it to get the values of 78, 29, 30, 90 in case you want to retrieve the values. So this is what is a structure that is pointing to itself, and that is what I just now explained here in terms of this. Now if you see actually what happens, so that's a rudimentary explanation. Here is what actually happens. Let's see this, and then this is the last topic of the day, which will introduce you to a linked list, right? So let us say that I have a node like this. I have defined a node like this. So the node structure says that there should be a data and there should be a next pointer, and the next pointer should be of data type node, that is self-referential data type. So the next pointer is also going to point to another node. So let us say that now I go to malloc and say that size of struct node, give me memory. Okay, so give me memory. Now tell me what is the memory. This is int, right? So this will take 4 bytes. This is next. It's an integer pointer. It's basically an integer pointer, which is basically a pointer is going to store integers at the end of the day, right? So it's also going to be 4 bytes. It's maybe a node type of pointer, but the amount of memory it needs is to store an address only. Now that address is of integer, so that is 4 bytes, right? So this is 4 plus 4 bytes called 10 bytes. So for every node, you want the compiler to give you from the RAM 4 bytes of memory. So you will tell malloc that malloc give me 10 bytes. 4 plus 4 is 8 bytes. 8 bytes of memory. So you will tell malloc that give me size of struct node. Whatever that node we created, I want the size of this node. Achha, you don't want to put the struct, assume that you will do a type def. Size of node, right? Size of node is what? Just now we calculated 8 bytes. So you can say malloc give me 8 bytes. And it will allocate 8 bytes. Right? It will allocate 8 bytes like this for you. Right? So this will be 4 bytes and this will be 4 bytes. It will allocate that memory. Let us say that memory is 1000 and you are putting that inside a pointer called N1. N1 is a pointer, means N1 will contain that 1000 and therefore N1 starts pointing to the block of memory that you have been given. Likewise, when you use the second syntax for N2, N2 let's say gets a memory at 4 bytes, that is 8 bytes at a memory of 2000 and therefore star of N2 is at 2000. And then if you see this as 3000 getting allocated to you 4 bytes and 4 bytes, right? So that is your N3 getting allocated, which is going to be at 4 bytes. So now N3 is pointing here, N2 is pointing here, and you are happy. Now you have got your nodes. Now you have to say that you have to now stitch it together. You now have 3 variables, but you needed an array of 3 different variables. You wanted to combine that into a contiguous area. So you want to create something like this. You want to create this pointing to this, this pointing to this. You want to create this link that is missing, right? Because you have now created blank empty structures. How do we do that? Right? So what we'll do is we will say that n1.data. So this is my data. First this is data. So n1.data. We cannot say n1 dot because n1 is a pointer. So to dereference, we will have to use n1 arrow. So we will say n1 arrow data is equal to 10. As soon as we do that, this will become 10. Right? So n1 means what? 1000. Arrow means what? Dereference. Dereference and go to 1000 and put the data value as 10. We do that. And n1's next, we also say n1 your next will be equal to n2. What is n2? n2 is 2000. So n1's next is here. So n1's next is 2000. So now we have built this link. n1 is now pointing, n1's next is now pointing to n2. We will say n2 arrow data is equal to 20. So then this becomes 20. And we will say n2 arrow next is equal to n3. n3 is 3000. So this will become 3000. So now it has started pointing to 3000. And we will say n3 arrow data is equal to 30. So this will become 30 and then the next will become null. We will say n3 arrow next is equal to null. So this is where now you have created 3 different customized data types, which is called as node containing your data, right? It is your own data type. And each of these data types are linked to the next value in the series that you want, right? Through pointers. And that's where you have created a linked list. Now, if you want to insert an item from the linked list, that's the way I said, right? So suppose you have to insert some item here. So you have this first N1, you have this N2, and you have this N3, and you want to insert an item. Let us say you want to insert an item here in between, right? So let us say that you have to insert an item. So this was your link. This was your link. These are your current links. So if you want to actually insert an item here, which is this, then what will you do? Now, you know that this particular person is pointing here. You know this particular person is pointing here. And you know this particular person is null. That is what you know, right? So what will you do? You will say that if I have to insert this element here, then the next has to point here. Instead of the next pointing here, the next has to point here. So I will remove this, right? And I will say that this next points here. And the next of this will point here. So that way the flow will be from here to here to here to here. So I now successfully inserted an item just by changing the pointers, right? And in your syllabus, how many pointer changes, etc. will come, which we will talk about, or I have already talked about that in the DSA lecture series. So that typically concludes what I wanted to cover. The structure holding the reference to another structure and itself, right? Self-referential structure is the most important topic if you have to enter into DSA, and that's what I have tried to explain here. I hope you have understood. That concludes this session, but needless to say, you can always approach me on WhatsApp, and the notes of this will be up on the description window. And of course, if you approach me on WhatsApp, you'll get responses in terms of doubts that you have. I'm not seeing any doubts on the live chat window, so I'll be assuming you don't have any doubts, but this will be also published as a live recording, so you can use the chat window there also to comment out with me, or use the WhatsApp link. Thank you so much for joining. Till the time we meet next, happy learning.